Hello everybody, welcome to another stream. How's it going? So we're on Windows today because somebody, as in me, bought a new GPU. So we shouldn't have any crashes anymore. The problem... Yeah, what's going on here? Is the stream coming through okay? I forgot to post something live. Right. It's coming through a little bit red, which is a bit of a problem for me. I don't know, I'm not sure if that is because we're streaming at a high resolution. I'm streaming at 4K and then I'm downscaling it, so I don't know. It seems it's okay here. But what about that bit rate? Too high. Or I remember it recommending it being. Yeah, isn't it 4,500? Oh, 6,000. Right. That's what I've got. Yeah, let's keep with 6,000. But am I coming through okay? Am I looking a bit more laggier than usual? Hey there, Ket. How's it going? Let's just zoom in on that one because it's clearly too small. I think if I... Or is there some properties I can change? I want to be able to like zoom in. If I interact. Right, it's not accepting any keyboard stuff. Right, so if I put it back to what it was, then let's scale it. Might be alright. Yeah, it is, isn't it? I'll let me put the property. Let's shrink this back. So what was that, 425? And damn it. So if we put it back to like the 1080p resolution, and then I'll just scale it by 2. So it might look a bit blurry, but right out loud. Right. It's on a wear my brain out trying to do maths. Right, 610. That's an easy one. Right. Cool. There we go, that's better. Yeah, that's good. Right. Yeah, I think the camera's got a bit of an FPS drop. I think it's the camera's at 4K. Yeah, I don't know what's going on for that one. It might just be to do with the camera. But although this is a bit laggy on my end. When I talk, are you guys seeing so this down here? Is this laggy for you? Like, does it look low FPS? Because if that's low FPS, then it's quite bad experience. Yeah. So I'm just concerned if this... Oh, okay, that's good, that's good. All right, I'm fine with the camera being low FPS. Maybe I can drop it to 1080p though. But I'll do that next stream. I can't be bothered to faff. So yeah, we're on Windows today. Why we're on Windows? Because I went and bought a new GPU. Because you know we had those GPU crashes last stream. We did more graphics, and I was thinking Let me buy a new GPU and hopefully we don't get the crashes again. So got an AMD 7600, AMD RX 7600. So I had the RX 6600, and that one was causing me those driver crashes. But when I put it into when I put the graphics card into my machine and tried to get my Manjaro OS running, it wouldn't boot. It would just get stuck there at the beginning. X11 wouldn't start up. X11 wouldn't start up, and it was a big issue. So I tried following some instructions online, like removing the graphics driver, and then it would say there's this package. Sort that wine. Okay. Then it would say there's this package I have that's conflicting, so I removed it, and then I sort of like removed the video driver, tried to reinstall it, and then it was like, I can't find that package you removed, so I manually installed it, and then it still couldn't find it. It was just super bizarre, so I'm like, screw it. I think I hosed my Manjaro install now, so I'm gonna have to sort of like reinstall that. But it's weird that it didn't pick up the driver right away because it's an AMD card and it's the same AMD driver. So like, why didn't it work? Apparently there's got to be some configuration that runs. So yeah, that was my yesterday evening, like faffing around with that. So we're on Windows for the time being until I can get a new fresh install working. And yeah, I want to test out this card, make sure that we don't have any of the same issues that we have before. If not, I'll just send it back. So yeah. Yeah, this was Windows, by the way. Oh, okay, interesting. Yeah, I'm just gonna stick with Visual Studio. I don't want to spend more time setting stuff up. But yeah, I didn't realize that. That's cool. It's pretty great. So, I guess I got to do a quick recap. So I did touch my computer a little bit more after we finished that stream, and I did fix that bug with the MSAA code. By the way, is this zoom level all right for you guys? Let me know if we need any more zoom, and I shall zoom. So effectively what the problem was is that the material calculations didn't come out well because the normal was wrong. So if you take a look now, we can, I don't know why it's so damn bright on this, on Windows. It just seemed like, I don't know if it's something to do with my monitor, but if I look at the previous stream, yeah, maybe we can look at the previous stream, we'll see how it looks on this monitor. It's just so bright. I don't know why. Anyway, as you can see, we can look at this ball, and we can go around it, and the normal seems alright because we're seeing the reflections in the material. So what the problem was there is that, and I might improve some of this actually because we're streaming at 4K, so these performance metrics are kind of at like near a 4K resolution. So what'll be interesting is if we actually print out the resolution that we're rendering these things in here too. But yeah. Yeah, so the problem was, so we're doing this sort of ellipsoid ray trace, so we're doing MSAA in software, and we've got this sort of approach where we calculate all the ray directions for each subsample. So MSAA will split your pixel into, you know, this is MSAA times 2, I guess. So it's got 4 subsamples, and we've got different ray directions, and this does a pass of over each ellipsoid and then over each subsample, and then tests against the ellipsoids. Now, I've been thinking about this approach off stream, and it's actually quite a poor approach, but let's just talk about what was wrong. So what was wrong is that when I did this multiply, the inverse, that was it. It was scaling the translation. So the object actually became close or further away than it should be, or something like this. Because whenever we got the hit value, the hit along the ray was wrong. So it meant that the normal that was being calculated after that ended up being further, always pointing towards the camera. So yeah, what I was doing is scaling so this ray versus ellipsoid. I was passing in the scale in here. So we had like e dot wad from local dot scale, but realistically the better idea is oh yeah, so I was passing in the scale in here, and I wasn't applying the scale when I was transforming the ray origin into the local space of the ellipsoid, and the ray direction into the local space of the ellipsoid, right? So imagine if you got your ellipsoid that's like this. The ray origin is then just relative. This is where the ray origin is. And then the ray direction is relative from here as well. Well, it's been rotated around such that this is axis aligned. So it may have been pointing that way, but then when it got rotated into the local space, it pointed that way, right? Yeah, now I scale these ray origins and ray direction, and I don't put the scale into here, and I've treated it like a unit ellipsoid. So you could think this is just a ray versus sphere then, right? And it kind of is, but the ray versus sphere, so essentially in the local space of the ellipsoid, it is ray tracing against a sphere. But the code that we were using, which is IQ's code, his ray versus sphere has an optimization in it such that it doesn't take into account a non-normalized ray direction. But because we're scaling this ray direction here, we still got to use that ray versus ellipsoid function because it takes into account like it does a few more. Yeah, here's the ray versus sphere. I don't quite understand the maths fully, so I can't really explain it fully. But here, you see, there's only a couple of dot products, but with you could probably ignore this, right? Because we're just doing divide by 1. But yeah, there's an extra dot product in here. Yeah, we could probably optimize this to say it's like, you know, a unit ellipsoid, and then that way we can get rid of those divisions. They'll probably be optimized out anyway, but it would just be better to do that. Yeah. Yeah, it's got an extra dot product in there, and it does some extra little maths here, so that handles like a non-uniform, a non-normalized ray direction. So yeah, but we are ray tracing against a sphere in the local space of the ellipsoid object in that case, because everything is the same dimension, length in each dimension. Visually, the text is a bit small for everyone watching the VOD at a lower quality, right? I'll jack it up a couple. I'm okay with that. Right, let's go to that properties panel. Cool. Thank you for that, Kip. Appreciate it. Is that better? Let me know if it's not. I don't know why it keeps showing up in red in my control panel. Oh, that's fine. Also green on the computer. I was talking about the which thing. It's showing up in red here for some reason. I don't know. Anywho. Oh yeah, I wanted to check the VOD. Because can you see my screen keeps like jumping around? Wait a minute. Uh, can you do that these days? You can. Yeah, see, it sort of gets very overexposed, and then it sort of like drops down. It's doing that, and my game ends up being constantly overexposed. So let's just look at the previous stream, and let's compare some colors. All right, not that one. Right, this is actually looking overexposed here. Oh, you can't hear the music. Ah. There you go. All right, thank you, Cat. Thank you, sir. Yeah, so this is looking much brighter on my screen. It might just be my monitor, actually. I don't know. Does past me look very bright here? Is this just my monitor playing up? Yeah, because this is very oversaturated. I think I haven't got HDR on, but it feels like there's something HDR like going on. Oh, then I scroll and it drops down. You're currently more bright as person, lol. Wait, I was in it. I'm currently more brighter. I don't know what's going on. Then it just got made brighter there. Ah, yeah, you can see it in the recording. No, but you can't see it as bad as I can. Right, I don't know what's going on. Solve that later. Anyway, let's get on with some actual work. So, right, what is good about this idea was bad about this idea from last stream. So, the problem is that this algorithm that we've written, this MSAA, is not going to be able to account for transparency. So, I was thinking maybe I should do a separate transparency pass and do a opaque pass first. But I think I'm going to backstep on that idea. But I was thinking, even if I was going to do an opaque pass and transparency later, this same algorithm that we've written, where we go over all of the ellipsoids and then go over every single subsample for every ellipsoid, right? And then sort of like we cache all of the sort of objects that have been hit and their weights. So like if an object gets hit multiple times, the weight goes up by 1, right? And then this way, we do the expensive material sampling here later on, but we do it outside of that loop. So the problem is we might have to, if we was to do it this way, we might have to introduce layers or something like this, and it's just weird. So I guess I can go for my yeah. So the thing about the current MSAA implementation, the way we do it, we do the for loops is problematic for transparency. We currently do loop over all the ellipsoids for each sample, check if we hit. If we hit uniquely, insert the ellipsoid index into the list, increment the weight by 1. Oh, and then, yeah, because we hit, increment the weight by 1. And then the second thing we do is loop over all the hits, sample the PBR material, and do the weighted average of those pixels. So we would have to stick this whole thing in another loop and do like layers of it, but then not really go over all of the ellipsoids. It's a bit weird. So doing it this way doesn't really work too well. So I've got another sort of solution, and that is we're going to instead do it as if we're going to super sample. So yeah, because we'd have to do layers Wait, yeah, so this problem, the problem with this is if we want to achieve transparency at all, this approach won't work as you need to blend pixels and we don't have the pixel color till later. Yeah. So this new solution is kind of like the way you do super sampling, but it does the optimization. So loop over each sample instead of each ellipsoid, right? And then go over every single ellipsoid, right? If we hit the ellipsoid, add it to a local hit list. If the local hit list is, if it's was yeah, if it's the first time it's going into the local hit list, append it to the list. Oh, no, sorry. Yeah, just add it to the loop. Right. Yeah. Okay, start that one again. For each sample, then for each ellipsoid. If we hit the ellipsoid, add it to a local hit list. So you're going to build up an array of hits. And these ones would be transparent. If you hit an opaque one, you'll just stop. Right? You just stop right there. You don't need to search any more ellipsoids. Or if your alpha goes to 1. And then if the overall hit list with all those hits is unique, you append it to a list of hit lists. And then you increment the weight for all the matching hit lists. So you could have some samples, subsamples. So here's your like big pixel, then it's split into subsamples. These two end up tracing against the exact same sets of ellipsoids. So they'll share the same list. And then like this final one is like loop over all the hit lists for each hit, sample the material and compute the weighted average of all the sample colors. So this is going to, so these two will end up just, the materials will be sampled once. And then maybe these ones are different. So they'll do their own sort of sampling, separate sampling. They have their own separate lists. But this will then be more optimized over just doing super sampling, where each pixel will basically just render its own. It will every time it hits something, it will perform a material sample. But the thing that this would do is that it will so the rays will shoot through the center of the pixel. You'll test against the ellipsoids which are in the scene, and all you're doing is testing which ones you hit, and you're building up that list of hits. Then later on when we do the material sampling, rather than having the rays that were through the pixels, you do it through the original big pixel, and you just take the depth that it hit at and do the normal calculation, then just do the lighting from there. So it's not going to be the exact same quality as super sampling, but it's obviously an optimization, which is what MSAA is. So effectively, this is an optimization to SSAA, super sampled anti-aliasing, and it's going to work basically the same sort of way. So what we're going to do is we're going to start off by doing a SSAA implementation because it's actually quite easy. It's just expensive to compute. So yeah, I guess we'll just get started with that one. Why don't we go to the graphics side of things, and when we print out that profile information, why don't we also print out the resolution? So we go scene dims, because we're kind of streaming at 4K here and rendering it obviously at 4K ish. So it'd be good to sort of like have that written down just so when we take these numbers in, we have something we just understanding what is going on better. So the scene dimensions is what we're under the scene at, because we can have UI with the scene inside the UI and not taking up the full screen. Then we have the surface dims, and this is what it's rendered to. Yeah, so why don't we just take a look at that quick. Yeah. Right, why is that? It's getting DPI scaled. Ah, I've got the zoom feature on. This is weird. So, is that what's going on? Is that why it's looking so bright? Interesting. So does this application do it as well? Got to be careful changing some of these settings while I'm streaming, I guess. But yeah, so I've got it at that, but I've scaled applications. So I guess you sometimes want to say don't scale these ones, but right. Because this one keeps blinking and getting so bright. Win32. Yeah, but then if I do that, or I set process DPI aware, we try and see what that looks like. And Brave browsers keeps blinking like crap. I should give that a go. We'll just drop it in the Windows side of things, see what goes on. Windows. There's a main in here, isn't there? Oh, right. That's now rendering at 4K, but the performance is way worse. Amy keeps jumping like that. It's quite terrible, to be honest. But yeah, it's still not fixing the problem. Yeah, we'll do that. So we'll leave that in there. I guess things just seem a bit overly bright. And it just flickers off. It just flickers off as well. What this does on my not sure if you guys can see it. I think you can. Yeah, I guess can you see this? This is my question. It goes. There you go. It's bright, then it's not bright. That one didn't do it. That one didn't do it. Alright, I guess not. Maybe I can get it open here. I can see it. Get my stream up. Alright, let's try that out. See if I see it. No, okay, it's a monitor thing. My monitor. I don't know why it's doing it. Doesn't do it on Linux. That's cool. At least it's not affecting the stream quality. All that matters. Alright, so what we're doing now. We're gonna do why am I in this entity gen stuff? Cool, so we're gonna take this shader. And we're gonna let's call this MSAA. We'll get back to this one, don't worry. We'll copy paste it and we'll do an SSAA, super sampled anti-aliasing version. And we'll obviously go over all of that one. So we'll get some new defines in here. And we'll be able to have a bit of a play about. So super sampled anti-aliasing. Now the problem is with this, it's gonna run so damn slow at 4K resolution, but oh well, let's just do 2 times for now so I don't like destroy my GPU. Alright, so we launched the compute shader full screen. This just gives us it so that every 4 threads within a wave is in a 2x2 like a pixel shader would do it. So you can use quad intrinsics and it's more optimized for yeah, it's just what GPUs are optimized for. And where's my music gone? Did I close Stone Rebel? Let's move on to another one. Then obviously if we go out bounds of the scene, we'll the scene text we're trying to render to, we'll just leave that one. SSAA, good. So we haven't really got a buffer filled with ellipsoids yet. This is not the main focus. The main focus is render ellipsoids that look good with anti-aliasing on it. So we've got a few implementations that we're going to write. There's going to be 3 versions that we'll write before we move on. And they're going to be separate shaders because they're going to have some specialized stuff, and putting all these if-defs in are just going to be... It's not going to be as nice reading the code over, so... Yeah. So, super sampled. We don't have an original... Yes, I think we want to get rid of some of this code. Oh, I want this one. I want this loop actually. Alright, so we'll get rid of these arrays though, which is great. Right, so super sampled scene dimps. So we're just going to multiply it by the dimension, a single dimension. So if it's times by 2, yeah, if it's, let's just say times 2, we just times it by 2. But on each dimension. And then we loop over over every single subsample. So here's our pixel of what times 2, we'll just be doing 4 pixels. And then we have a times 4, we'll be doing 16 pixels. Like that. So it gets expensive quick, right? Then we get our super sampled anti-alias coordinate by scaling it up by the dimensions and then adding the offset within the subpixel in the within the pixel, right? So give us that subpixel coordinate. Then we compute the ray direction for that given pixel based on where the camera is. So you got yourself a view frustum. Your sort of near plane will be, or the texture will kind of be like kind of here, right? So we're rendering to, and it'll give us a ray direction that shoots through that pixel into the world. And this will be done in view space. So it's a view space direction. And then our ray origin is at 0. So this, what is this doing? Yeah, then we multiply it into world space. Okay, so after we've done that, we want to go over every single ellipsoid. And we want to get we just do all this sort of stuff. So, hang on a minute. So, we go over every single ellipsoid, which again will improve that code later on. We calculate the inverse transform. We transform the ray origin, which we don't have. Oh, the ray origin, we should have kept that one. Hang on a minute. Let me go to the that code back. Alright, so what we're missing is a bit of this. Right, so the ray origin will be the same for all the subsample pixels, just the ray direction is different. So we translate that ray origin into the local space of the ellipsoid object. And this does translation, rotation, and scaling. So we go from world space to local space. Then let me just find some of the other code. Then we translate the direction as well, this time just scale, and rotation into the local space of the object. And then do a rayverse ellipsoid. Now we pass in as for the extents 1 for every dimension of the ellipsoid. So the ellipsoid will be axis aligned in the local space of the object. And it would also be just basically a sphere. So we just put it all to 1. We have to still use the rayverse ellipsoid function. We can't use a rayverse sphere because it's got some special things that account for a non-normalized ray direction. And this will return us a near and far. I've still got to handle this properly. We can look into that, I think. How we want that to behave. We can have a think about that. But basically, if the far is greater than 0, then it means that we are at least inside the ellipsoid. Right, and then what do I want to do when I've hit the ellipsoid? I want to. So I don't want to do the sampling here, because if I do the sampling here, there's a problem. So I need to keep track of all the ellipsoids that we hit. I need to make a hit list, I think. And you probably want to have like a maximum. So we'll define up here SSAA hit list capacity. So say we said 8. That's 8 registers that we're going to be using in this loop. Yeah, so we're going to be careful about how many registers we use, because the more registers we use, the less compute shaders that can run on the same compute unit and pause and swap out for other ones. So we've got to be careful. So let's just say there could be at most 8. Maybe it's a bit too many, but like 8 layers of transparency, basically. Yeah, 8 layers of transparency. That's probably quite a lot. Maybe you could get away with 4. But yeah. Let's just do 8 for now. So yeah, we're just gonna say, so we need another register. Say hit list count. So you go if no, so I guess you say hit list count. We'll say equal to e index. We hit this ellipsoid. Then we'll increment the hit list count. And then check, hey, if the hit list count is greater than or equal to then we'll just break early. But we also want to break if we have reached fully opaque, which we don't know yet. Oh. Because there's some optimization you can do if you're ray tracing from front to back. You can know if something is fully opaque, but so where will we get the transparency from? Oh my days, what did I do? I pressed buttons. See, there's a material index, right? So if we have opacity as another one, we'll use a full-on float, but we'll obviously quantize that down. So if we keep track of the alphas, we can know when we have hit something that's opaque or hit enough transparent things that it's become opaque. Yeah. So we'll be able to do that. And then we can early out basically on that. So we'll be able to do that here. Right. I'm just going to take a quick little break. I'll be back in a couple of minutes. Right, welcome back everybody. So, yeah, I was doing this sort of like, if we hit the ellipsoid, I was going to accumulate the alpha. Yeah, we're optimizing early, as you do. So, effectively, when you start the ray trace through one of the subsamples, you build up some alpha. You call it ACC, as in accumulated alpha. Start off at 0, I guess. And what you want to do when you get a hit is do that sort of I've got a front to back blend function. You want to do whatever this thing is right here. I guess I can say front to back blend. Right, we can just make a function for it, right? As you do. So pre-multiply. What? There we go, one of them. That's what I want. So it's quite cheap to do that. It shouldn't be that bad. Although we're doing quite a bit in here. Be careful. Like we're inside an if statement here. So if see on each thread in a wave gets a big pixel, and then that big pixel goes over all the subpixels. So like each so when there's an if statement, it means that the ellipsoid that is currently being looked at for each of those waves, they better all be having having a hit basically. If not, you're gonna have quite a lot of inactive threads in here. You got to be careful of that. The front would be the previous alpha, and the back would be the new one. So it's E dot alpha. There we go. Good, isn't it? So I guess we'll put in here dot alpha 1, and we can have a bit of a play with that. Yeah, a bit of a play. Have a bit of fun. So you do the blend. So if alpha is greater than or equal to 1, well, we've finished, right? We don't have to search for any more ellipsoids. So again, when you hit this break, your thread is going to become inactive. And so if there's any other threads within a wave, right, 32 threads, they will still go around in this loop. So you sure hope. So they're all going to be within the same tile, which then also guarantees they have to search over the exact same ellipsoids. So that also means yeah, and because they're checking the same ellipsoids, they should hopefully like only diverge, yeah, they'll only diverge around the edges of the ellipsoids, basically, that being rendered. So yeah, so something you got to be careful about. So we could probably, whenever we like bin these ellipsoids into screen tiles, we have to make sure that the tile size is at least 8 by 8, and if it's any smaller, it's going to impact the wave this loop, and it will get really bad performance because of that, probably. Or we'll get worse performance than it already is by this branch. But it's quite, yeah, and these breaks here make them inactive. Right, so we're adding to that list. Doing the blend earlier now if we can, which is great, cool. I think that's, we also want to record like a depth as well, probably like at what depth did I hit this thing? So we can then reconstruct. So So we can then reconstruct the hit depth would be T near. So we can reconstruct the normal and do some good lighting. Right. So now that that's done, we'll do the more expensive calculations here, and we'll get into why that is. Let's just get the code in. So into the material sample. And if you missed, you want to do a sky sample as well, isn't it? Yeah. So on these things, I think. Yeah. Right, so after we've gone over all the ellipsoids, we want to do the expensive operations, which is doing the material calculations. So we're going to go over all of those hits. Hit list count. Yeah, it could be a better name, to be honest. We call it entries count. Then this one is probably better off being ellipsoid indices. And that should be pluralized as well, it's a list, right? Cool. Much better. So yeah, we want to actually extract the values out of this array. Cool, so this would be the depth, the hit depth. This would be the the ellipsoid index. And then we can get the ellipsoid again. And then we can calculate the closest hit position. Then with that, calculate the normal. This has really got to be cleaned up. Yeah, so we want to get what does this get? This gets what's known as the vector towards the this would be like closest hit from ellipsoid vec. Closest hit from ellipsoid vector in world space. Closest hit from ellipsoid vector world space. Bit long, but hey. Then we're passing the scale as well. And we just called this one E. Yes, I'll calculate us the normal. Then with the normal and the view direction and the surface. So the view direction is a normalized vector towards where the view is from the surface. And then a surface position, right? So it's the hit position, and then the normal for that we calculate here. And then we unpack our material, which for now just has the most basic PBR stuff. So albedo, emissive. We still can't see emissive in terms of bloom. We've got to add that in. But yeah, roughness and metalness. We can get more in the future, but for now, we'll just do these ones. And then we calculate the surface color, which is expensive. There's a lot of samples and maths calculations. So the reason why you do it here in a separate list is because remember when I said you better be careful that. So on GPUs, if you take a branch, you have a wave of 32 threads, and that is just it's not really threads. It's 32 wide SIMD SIMD basically. So each if not all threads take this branch, you're gonna have inactive operations that will happen when it does the when it uses that ALU of the compute unit. They're going to be doing they'll probably do operations on it, but it's going to be I think they're masked out, isn't it? Yeah. So they're just going to be wasted basically. They're not going to be used for those threads that haven't passed this condition. So if I was to put the material sample in here, this is a super slow calculate surface color, and this is way quicker. So threads are quite likely to be more likely to be inactive in this area. So we'll put them out into a separate list, and then later on, we'll go over those entries, and this number are they more likely? Or maybe they're not. Maybe we can stick it in here. Because so they're going over the same list. Yeah. Yeah. So they might hit different ellipsoids, but they still hit the same number of ellipsoids in different threads. And then this is, so say if you have like, this is a good example. You have 2 pixels, right? These get their own thread. And technically, they're doing subsamples, so they're actually split. And they're doing one subsample at a time. So imagine if like this has got one ellipsoid here it's ray tracing against, and this has got a different one that's ray tracing against. They're still going to both hit one. They're going to hit different ellipsoids. So what we're doing is where they hit the different ellipsoids, this will be cheaper, it'll stick in a list. But then when they get down to here, they're both only going to be going over this once, and they'll do this expensive operation together at the same time. Yeah, together at the same time, meaning that we'll have less inactive lanes in this one overall. So that'll be pretty good. We're also missing the fact that the sky calculation as well, but let's just get to the main meat and potatoes of super sampling. Then we'll put the sky in there, because if you don't hit something, you don't become opaque, then you gotta sample the sky. Yeah, so effectively you can have this sort of like, I'm running HLSL there. Final color. Your final color is going to be start for 0. And all we're going to do is every time we go over a subsample, we're going to add to that color. Wait, we don't need alpha. Do we need alpha? No, we'll keep the alpha in there just in case. We'll add what's known as the subsample color. Right. And then after all of these, we'll simply just divide final color by the number of SSAA samples. So that's just taking an average. Then how do we get the subsample color? Well, we've got to do a weighted average. No, not weighted average. This one is front to back blending. So this would be, you start off as opaque. No, yeah, I think it's just fully transparent black. I think so. Just double check. This is the UI render. Front to back. Yeah, you start off as, yeah. Cool. So subsample color. So if you sample the color of the surface, then you say blend pixels front to back. So the front would be the subsample color. Don't know why I didn't pick that one up there. And then we also want to do, so we put in that C, C.x, C.y, C.z, mixed in with the E.alpha, right, the alpha of that ellipsoid. So I do the blend, the super lovely blend, and voila. So we're actually missing the sky. So we need to say if the ellipsoid, no, if the accumulated alpha, I guess you don't need accumulated alpha anymore. Oh. God, I called it accumulated alpha, didn't I? Because we could say goodbye to that register there. If we reuse it, it keeps the lifetime. Because we would have recalculated it again in here. So we don't want to use, we want to use this one such that it can throw that register away. Right, it doesn't have to keep that variable alive. It can reuse it. So if this is less than 1, it means it's not fully opaque, which means you need to do a sky sample. So that's this one here. Some code I made earlier. Oh. So we'll just sample the cube map given the ray direction in world space. And yeah, I got this thing here. It's the texture's currently in sRGB. So it's not a good idea to sample it probably. It needs to be a HDR texture. But anywho. Then we're doing some, we'll front to blend it. Front to back blend. The environment color. Just like that. Cool. So I think that's it. Let's delete all this old MSAA code. Well, we've got it copied on the other shader anyway. Final color. Right, then we can take it from linear and put it to sRGB because we haven't got a HDR target yet. That's something to do very soon though. And then we output the final color. And there's a closest hit here. So the closest hit, I've not got one of these guys. So how do we do that? Well, I think we do something like Closest hit T world space. Initialized as infinity. Then what we need to do is, I need to find a good way to insert it, but it's effectively got the depths in here. So you've probably hit something. Yeah, I can't find a better way around it, but we need an if statement. Because we'll get some uninitialized memory if not. Well, yeah, we've got to put the if statement in. So we've got to say if hit list entries count. You have something in there. This equals the minimum between this and the hit list depth 0. Boom. So then that will be, yeah, that'll go out in the depth texture, and then the output texture get obviously the final color. So let's just double check this whole shader, make sure the logic is all sound, and then we'll give it a run, see how terrible and slow it's going to run, because this is super sampled anti-aliasing and we're running at 4K on a mid-tier card which is only really built for 1080p, but that's cool. So what have I got? I recently just literally bought this and installed it last night. 7600. I went from a 6600. You know, there's one I used to have, but what happened is it would crash and burn my whole desktop environment and blue screen Windows at least. Blue screen's Windows, and then on Linux it would crash the desktop environment. It's 8 gigs of VRAM, 28 compute units. And then I went and just got the next generation one. So I paid £230 for this one, then sorry, £260 for this a couple of years back. And then I paid £230 for this one. I got the Sapphire version. Apparently it's overclocked. And apparently this one's got a few more compute units. And apparently it's 30% better overall. I think it's got some other, obviously things are not, there's not just like one metric. There's many metrics to a GPU, but overall it's about 30% better. So, and also uses more power in the process. So, yeah, I don't blow the bank when I buy hardware. I'm quite a cheapskate, to be fair, but it's good to develop on a mid-tier machine at least. So yeah, let's double check this logic, make sure it's all sound before we fire it away. So we've got our ellipsoids, we've added the alpha channel now, we'll have a play about with this. They're sorted front to back because we're going to tile bin these things. So each tile has their own little list of ellipsoids, and you're going to have all your threads within the same wave are going to use the same tile and check that list. They're obviously not going to hit all those ellipsoids, but they'll be, but you know they're close by, close enough by. Yeah, so we're going to start off with a 2x2 SSAA dim. I guess you could start off, you could do a 1 as well. This does turn off. Any reason AMD over NVIDIA? Yes. I'm not really a fan of the direction that NVIDIA going. It's like AI, hardware ray tracing, you know, more black box stuff, right? I'm not a fan of that. Like, if they're going to be doing hardware for ray tracing, if they're going to be doing AI, at least give developers access to it. In terms of like, it's this particular piece of hardware where you can, you know, it's got these either these sorts of like intrinsics that you can use, right? Or you know, a bit like how you would think of like an x86 CPU. You just program it, you got assembly for it. That's the interface. I don't think I don't like these high level interfaces for GPUs. If they're going to be adding more hardware, then yeah, if they could expose it better, that would be, I'll probably be okay with that. Yeah, they're also like really into yeah, just chasing the AI hype train as well. And yeah, they're not really going towards the sort of more open stuff. What I like about AMD, even though I did buy a card from them and it had that major issue with it that I did live with for some time. I'll give them the benefit of doubt one time, and if it messes me up on this one, I want to change to something else. I'll go Intel maybe, or maybe Nvidia. But they do open source stuff, so they you know about like AMD Open, GPU Open. Might as well call it AMD Open, but um, you know, they could be more open source. I wish they were more open source, but they've got this like Fidelity FX SDK where they've got like tons of things that developers can take and put in their engines, MIT licensed. You just have to say, hey, AMD made this thing. They got tons of things, so just got to find them all. Yeah, they got contrast, adaptive sharpening, denoisers, ambient occlusion stuff. Parallel sort, we actually use this one, and we're going to be using it to do the tile binning stuff soon. Just pour it into over to HCC in my custom C compiler, and just just worked. Single pass down sampler, which is pretty cool. So you don't have to launch all different compute shaders. You just do it all in one pass. You got FSR. You don't have to. Yeah, you can use that. It's actually quite a lot of code. These things at FSR. You look into it. The frame interpolation thing apparently was FSR, isn't it? Depth of field, blur, Brixelizer, which is like a voxelizer of your voxelizer, basically a Brixelizer GI, and they've got that sort of AMD GI thing as well, isn't it? They've done, but yeah, they do a lot of sort of like research and graphics and open source it for people to use in their engines. To do a lot of research for people who make engines, which is really cool, and I would like to support them for doing that. Yeah, I wish they were more open, though. Why don't we have their shader compiler in user space and be able to compile our binaries and give it to Vulkan? Why isn't there an extension for that? It just seems like I don't know why we don't have that. They have the ISO open and available, but it would be good if you could at least have the option to ship that, or while you are at least making an application, you can compile it and see what you get. A little bit easier without having to use specific tooling or something. Get a peek behind the curtain a bit more of what's going on, basically. But yeah, that's why I like AMD more. Intel's the second best because of that. They're reasonably open as well, but their hardware is not as good, is it? But I haven't tried their latest GPUs, to be honest. How Intel makes two types of cores, one CPU. So I chose AMD and JRC and loop of fast instructions on. I've not heard of that. JRCXZ. Ah, jumping condition is met. Hmm. Yeah, but you've got. Oh, I see what you're saying. So, like on Intel, your one set instructions is CPU. Yeah, but you need. Yeah, I don't know. Maybe you could get it to work, but you'd have to. Yeah, I imagine you could maybe get a subset of x86 to work, but I don't know how much the sort of model of x86, like the memory model, and how I don't know how much, and like the branch predictor and how the CPU works ties into the instruction set. Maybe it doesn't, to the point where it can affect things. Maybe they could use a subset of x86 for the GPU. I don't know. That would have been interesting, because then you wouldn't have to learn another instruction set. Well, they don't have this on the Intel one. Yeah, that's the thing. Is like you can't branch on GPUs typically. I think some GPUs have support for it. Oh, they're still on Intel. CPU is AMD as well. I guess it could be called an AMD fanboy, I guess. Just, yeah. Prefer them a bit at the moment. I haven't quite got an AMD t-shirt though. Maybe I need to get some AMD merch. So yeah, I guess let's just double check this SSAA, super sampled anti-aliasing code, is sound before we launch it and try my GPU. Yeah, so that's all good. We added the alpha. We'll test that out. The sort of front to back. We get the ray origin. It's the same for every subsample. So you just, it's obviously 0 in view space, and then we move it into world space. We get the SSAA scene dimensions. So how big is I want to move it like that so it's all ordered a bit nicely. So just multiply it by the number of dims. This is 2, so we just multiply the scene dims by 2. So that's the super resolution. Final color is initialized to 0 in all components, and the closest hit is infinity. Now we go over every single subsample or subpixel. Subsample, and we say samples per array, is terrible naming. You're not just doing one texture sample. Sample can be taken for array. So just be wary of that when someone uses the word sample. This is just the wonderful wording graphics has, like, yeah, like the word buffer can mean a texture, like a depth buffer, and textures are just images, but no one likes to use the word image. Yeah, graphics programming names. There we go. So we then calculate this super sampled coordinate by multiplying it by the dimensions and adding the offset. We then calculate the ray direction in view space for that given super sampled so the ray that goes through that subsample, that subpixel, in view space, and move it into world space just by scaling it and rotating it. We set the accumulated alpha to 0 and the hit list entries count to 0. So why don't we make this 4? I think 8 is like far too many. I want to be careful of my registers, So we've got 8 registers being used between these two at least. 9, 10. And then like how many here? Got to be careful. I don't know if these can probably be recycled because they're only used up to here anyway. So can that one. So you just have these ones. Yeah, the lifetime of these two variables are very short. So we go over every single ellipsoid, that subpixel, ray trace against them. If we do, by transforming into the local space of the ellipsoid, which is basically a sphere, because it does all the scaling and everything on the rays instead. And then if we've hit the ellipsoid, add it to the hit list because it's the cheapest operation. And then blend the alpha front to back so we know when to stop. And if we fill up the hit list, just stop there, and we'll accept the error. So if you fill up the hit list, more than 4 layers of transparency, you will not see anything else behind it, and it will be blended with the sky, which can be a problem. But if you have 4 layers of transparency, you sure hope you've hit something by then. You should have. There's quite a lot of layers, or it should be quite opaque at that point, right? Maybe seeing the sky won't be that bad. Anyway, so then we go over all of our hits in order from front to back. Subsample color equals 0. We go over the hit list, get the ellipsoid index, get the hit depth, and calculate the hit position in world space, calculate the vector that goes towards the hit position from the ellipsoid center. And then we calculate the closest hit normal. We pass in the normal and the hit position into the shading structure, which gets passed into calculate surface color when it passes in the material and the shading structure, which just holds a bunch of context while we call a bunch of functions. So I can pass a structure around instead of passing a bunch of parameters. So I got some inputs, the view direction towards the camera, from the surface position that was hit, and the surface normal. Then we've got other things that is passed around. Yeah, we're going to add support for more lights and stuff like this, but that'll come later. Yeah, then when we get our color information, we blend it front to back with this guy. Then if the alpha is still transparent, we just go right, get the sky, blend it front to back with that. If we had some hit, right, I don't want to put it in that loop because it will keep doing the check. We'll do a min with the closest hit, and the front one is the closest hit. So you're going to get the transparent. This is kind of the issue though. You'll get the transparent one. So we say, we'll put to do here. Do we want the transparent front ellipsoid, or do we want the opaque back ellipsoid? Right, it's a good question. What do we want in there? Maybe we want both in different textures because they might be useful. Different post or operations that run deferred on that thing we've rendered. So then we accumulate the each subsample of the main pixel we're trying to render. We accumulate the color into final color. Then after that lovely for loop that we just went over, does all the subsamples, right? Accumulates into final color. Then we simply just divide it by the number of samples, take an average, and then convert it to sRGB. This will go in the future because we're currently going out to an sRGB texture. And then we put the depth out as well. That is sound. Pretty sure it's good to go. So we'll look for ray tracer, and we'll throw in it SSAA, and it just launches it full screen, passes in a couple of textures, does some sync code, and that's about it. So here we go. Chances are this is going to make my computer go crazy because it's very, very expensive. Nice. Huh? Yeah, we're on Windows now. I'm a Windows dev. Alright. But it looks so good. Eh? Okay, front to back. What have I done? Explain. Is there no such thing as F32? What compiler are we in? Is this a my compiler thing? I think this is a my compiler thing because it didn't show up in the error list. My compiler doesn't respect Windows, I guess. So, what's my compiler complaining about? I don't suppose a dot. Is a dot? A dot. Ah, there's a dot A, isn't there? On a float. Of course. It works. It's alive. That ain't bad speed. That's better than the, Are you seeing this? That multi-sampled anti-aliasing we was doing was like 7 milliseconds at this resolution. I guess we were using so many registers on that multi-sampled one that we tried. It was just so... It was unable to schedule a lot of them on the compute units. And this is doing 4 times... Sorry. Yeah, 4 times the number of pixels as this, but it's 2 times the resolution. And obviously it's keeping it all in memory. Ain't too bad. Obviously we're not got that many ellipsoids, but for this type of card that we've got, quite good. And we can have a play with... Yeah, so with Clang on Windows, right? I think if you install it... I think I installed one through the Visual Studio thing. But Clang knows if it's running on Windows, so it will output its error messages in a Visual Studio friendly way. So it uses brackets instead of colons or something. And then it shows up in the error list. My compiler doesn't do that. You know, you would think that Visual Studio, being a very feature-rich editor, would support different ways of having errors show up. Like most text editors do that parse the output of a CLI program. Right, that performance ain't too bad. I guess, should we have a bit of a look around at the pixels? So we've got the screenshot tool. What's going on with... Oh, my laptop decided it's gonna lose internet connection. Oh, I just closed the web browser. Back. Right, so those... I don't see no jagged edges, but we are rendering at 4K. Let me hit that button. Shoot. The screenshot tool don't work on Windows. What's going on here? NTDLL. My favorite. Want to help me out here, Windows? Is there more threads? It's like debug, isn't it? Main thread. There we go. Right, call stack. Alright, what's she complaining about here? The root's here, which means it's probably here. Or around this. We can't tell. I did run the weight 7.4s, right. I've got the validation layers on. I think so. Yeah, so if I have the source code to the layers, it might be a bit easier to debug. That's a shame. How doesn't that work? Well, let's try that again. It was looking pretty good though. I can't see jagged edges. How come I use Windows when it's not open source? Because I don't use Windows. But what's happened, but I have it around so I can port my game to it. But I installed a new GPU and my Linux install decided to crash and burn when I inserted the new GPU. So this is why. I need to reinstall it. What did Linus say about PCs? Why am I not using signed num integers? Because I like unsigned integers. I don't like the extra invalid state. It's a big thing. But if I need a signed int, I'll cast it. So we press F12, it crashes. Oh, it doesn't crash. For crying out loud, it's a break. It's right. I need to Right, I'm so glad I remembered that's a feature. It's not a bug. Right. It's a feature of Visual Studio. If you press F12, it literally debug breaks the program you're running. So if I change it to F11 instead. Oh man. Wait, can I disable that? Visual Studio disable F12. Why is my damn laptop? Right, I'm gonna restart my laptop. Through this thing. Losing Wi-Fi. Settings. Developer. Oh. Yeah, it's called pause, isn't it? Or break. I like the F12 key. Some people say if you're using too much RAM, you can like... Huh? Oh yeah, I think they were trying to think of some use case. I don't know, I wasn't reading it properly, probably. It's probably, if I just go into the settings, I could probably find it. Right, I thought that would be it. Not it. There's probably under the keyboard key shortcut things, whatever they're called. Windows. How'd you change that? Tools options. Use keyboard. Already in there. Right. The fact that Windows, you hold Control and press backspace and it literally inserts a backspace key. Or whatever that is. Why can't you search by... Probably called pause. Or maybe it's got break. I could just change it to F11. Right. I want to find it there. I guess if we run the application and we see up in here, we might be able to find what it's called. Screw it. We'll just change it to F11. Extremely sad though. So press F9. I should press the F11 key. What am I doing? Right, let's get rid of that insert. Right, this will take a screenshot. Well, I'm using Windows because Linux decided to die on me when I installed a new GPU, even though I already had the drivers installed. Oh, so the game crashed. Right, so now it actually crashes somewhere in the readback texture. Oh, it's just bigger than the readback buffer. Right, up we go. 64 megabytes. Here we go. Yeah, so I already had the AMD drivers installed. I took out an old AMD card, put another one in. Didn't work. I've spent ages faffing about with different commands to uninstall and reinstall the drivers. And then it wouldn't allow me to remove it eventually, and then it actually wouldn't allow me to install it again. So I'm gonna have to literally try and reinstall Linux now from scratch. Sucks. Right, there's one screenshot. That took time. But it worked. Because here it is. Wow, my UI is so small. Right, look at that. That's the anti-aliasing. So that looks quite right, doesn't it? This is only with 2 times super sample. So, you know, we are running at 4K though, so one would be yeah, the pixels are a lot smaller. What else do we want to? Yeah, this UI is so damn small. I do not. My application is actually not DPI aware. Although I was quite interested in its rendering at high resolution. I could set DPI scaling, but I have to get the DPI scale from Windows. I've got it in my UI system, but I've never tested it. Yeah, we'll leave that alone for today. Anything else I want to do about this thing? What's this? I did input some new validation layers on. Right. Ah, we got no handle. Where? In the destroyer? What destroyer? Right. When I added this. Oh yeah. I thought I had things around these. What did I do? I said so if we don't have any of these initialized, just don't chuck it on the deferred delete queue. Nice. Right, so should we try and up the resolution even further and just see how well it runs? Because I would be interested in seeing that. So let's go to. So what did we get again? We got about like 1.3, 1.4, 1.4 ms, rendering 2 times this resolution. Right, we only rendered a couple of ellipsoids, but that was much better than the other one. Let's do make it 4. It's got to be power of 2. There's not many more optimizations I can make to this. I don't think. Well, we can obviously optimize the material thing. We can see like how slow is the material code by just commenting it out basically and just seeing what goes on. Yes, this is still running all right. So this is at 4 times the resolution, so it's doing 16 subpixels. It's running about 4.7 ms. So you about 4 times less than 4 times slower. So the best thing about this is it's not running out to memory. It's doing one ray, right? Going through all those ellipsoids, early's out when it hits something opaque, then goes over all the ellipsoids and actually processes the material color front to back. And then it will just add the color on to the final color. And then it'll go to the next subpixel or subsample. And then it will so the only things it keeps around are these variables here versus all the variables that's made inside. So yeah, we get a lot of yeah, we don't keep a lot of information in the outer loops. It's great. That's pretty cool. that will scale quite well. That shader will be able to scale as high as we want to, basically, without making another specialized shader. Let's just change this color to something like, let's just say all it gets back is red. So it's not going to do any material sampling. Let's just see how well it runs, and just to show you how expensive the material calculations are. There you go, beautiful red. We take a look. Performance. Right, actually, this is kind of jumping around a bit. I should double check. Right, this is about 3.8 on average. 3.8 worst case. Right, let me put it back and we'll find what the worst case is. So the problem is I'm streaming at the same time, so I don't think we get a stable. So yeah, one thing to note is these times are worse, and second thing to note is sharing it with OBS. It's a 4.7, 4.7. Right, so we're looking about 1 millisecond cost for currently, but it's not a good test because the that's actually quite stable. But yeah, we're yeah, that was at 4 times, so 16 subsamples, and that is only with 2 ellipsoids, and every pixel that hits will render only one, and we'll only do 1 material sample. And there's a lot of pixels which are not doing any material samples, they're just fetching the sky color from a texture. So that's something to note. We're not filling the screen with those at the moment. So I guess when we get closer, take a look at that number. Alright, full screen. This is a better number. Let's stop it there. Huh? Oh, did that close my window? No, it didn't. Good. Right, so about 8 milliseconds. Right, now we're talking. You will kind of expect this, right? It's not a good GPU. It's doing it kind of like 4 times some kind of 4K-ish resolution. So that's all right. Cool, so that's super sampled anti-aliasing. Let's go ahead and do the more sort of, or hopefully more optimized version, which is multi-sampled anti-aliasing, where we're gonna, after every single time we see which ones we've hit, we're gonna try and avoid doing this material sample per subsample, and bring it outside and share it between all of the subsamples. Right. So it's gonna be pretty cool. Let's take this one and override the old one. I don't want that in there anymore. This is the old MSAA code. Ain't good. First draft. We've got new ideas. But so multi-sampled anti-aliasing. So I can do a quick recap on what MSAA is. I will fix it. I will fix it. I'll get back to Linux very soon. It's just, it literally broke last night. So I had to be like, crap, I want to stream tomorrow. So, you know, Windows was there and Windows worked. You know, it's a shame to say it. Linux, when you take out a GPU and plug a new GPU in, even when you have the graphics driver installed, for some reason, it didn't work and I had to do something on the command line. I did something on the command line, and it it let me uninstall my graphics driver, but because of the Pacman package manager and whatever command, it wouldn't let me reinstall it again. There's something fishy going on, and I couldn't figure it out. So I'm just gonna reinstall my desktop. Oh my, yeah, Manjaro probably again. So multi-sampled anti-aliasing. Let's start with a 2. Right, we can. Oh, we didn't even check how good a 4x4 looked. Hang on a minute. Let's take a screenshot and compare how well a 4x4 looks to a 2x2. Right, here we go. So we do that Alt F11. That's an alternative screenshot. And then we can press F9. Here's the old one. Right, look at those edges. Now here's the new one. For crying out loud, it didn't work. Same, the new one. What's going on? Alright. This is what the old one looks like. I don't know why it didn't work. How do I fix this? Image view ain't null. What's it saying now? Image already destroyed or something. Oh, it must be a valid handle. I don't know where it came from. I could pass in some file and line information, but that's probably not going to help because it's abstracted anyway. So I could have just passed in the original resource. I could pass in a name, which could probably help. This is named anyway, doesn't? Oh, but it's not valid anymore, is it? So object type instance. No, that's just the instance complaining. You just pass in the device, right? Okay. Right, I know what's going on. So the problem is I used to delete the old. I used to set them to null. I know what's going on. I used to set them to null. When I deleted them. Which then became a problem. Right, which ones are doing it again? Yes, I want to say if they're static. No. Right, I got an idea. Clear handles. So yeah, the problem is some of them want them cleared, others don't want them cleared. Because you clear a temporary resource. Wait. I forget now. I forget which ones want them cleared. We can figure it out. Image view. Some of them need them to stick around. Probably don't want the early return in that regard. Nice. So what do we call this? Let's hop to this one. Hey, we don't have you anywhere. Okay, that's fine. Why don't we have that anywhere? Ah, it's not searching entire solution, right? So these aren't included in the solution. So I want to say current direct. No. I want to say search in. They're not added to the actual project, but I've pressed a button so I can see all the files. So yeah, I think I just need to hard code something in here. Access folder. Anyway. There we go. Yeah, Parse Henry messed up. What can I say? Is far inferior. Except sometimes Parse Henry knew what he was doing, and then Future Henry forgot. And then, you know. But in that case too, it's Parse Henry's fault, because Parse Henry should have known he would forget and jot down so that Future Henry could remember. So yeah, it's always Parse Henry's fault. Always. Yes, so when we get rid of temporary resources, we actually want to clear those things down to null. Yeah, so the next frame, even if they're not initialized, I think that's ultimately the problem. It won't try and recycle them again. Is that right? But then you don't want to be recycled if it's a right, okay, so maybe you don't need this. Right, I got it. So you only want to do this, providing that resource mem state is GPU mem state allocated. It was allocated, which then means the things are initialized. Okay, I got it. So I don't need that anymore. Means the code should be a lot easier to understand. I can undo all this. Get back those super lovely early returns. Alright, that'll do it. So I think I pressed F9 and I opened up the text view and then I closed it. Can I do that? Yeah, good. Right, still works. Right, so let's take that screenshot. I want to take Alt F11. It's not taking it. Right. I did Control F11 again. So we saw what it used to look like. Anyway, the screenshot's been taken. Let's just take a look at it. Yeah, so here's the 4 times one. As you tell, this is more of like a proper gradient, right? The other one, the 2 times. So when it was just a pixel split instead of 2 by 2, this would be like these 3 pixels are all the same color, and these 2 are the same color, and those 2 are the same color. So it just look like very horizontal strips. But this now looks like it's more of a smoother gradient. So that's the 4 times. So that's 16 subsamples. It's quite a lot. But yeah, let's make that. Look at the graphics. Or press 11. I don't have this alt thing working apparently. So I guess I'm changing it again. So F10 will get you the first one, then F11 will get you the second one. Right. There we go. So now we can actually compare screenshots. Going to be useful. Right. So back to actually write some shader code. So we're doing a multi-sample anti-alias now. So let's go to that one. So MSAA. Just start for 2 times. So this, I've just copied the super sampled anti-alias one. We'll just make that better. So let's quickly recap what MSAA is. So MSAA is an optimized super sample anti-alias. So here's a pixel you're trying to shade. In super sampling, you'll in a 2 times 1, you'll split it into a 2 by 2, whereas you have 4 subsamples, and you'll essentially just render 4 pixels, then take the average of those, and then that will be your final color. So it's just like downsampling it, right? An even downsample. For multi-sampled anti-aliasing, it's kind of an optimization of that. So instead of rendering it at, you could say that instead of rendering at the full resolution and running the quote-unquote pixel shader at each of these locations, instead you only run the pixel shader once, right? It's the expensive pixel shader once. And you're filling up these pixels, in a sense, with that same pixel shader invocation. So imagine, so in triangle speak, which we don't render triangles, but if you had triangles that overlapped something like that, and you had another one that did something like this. These are your sample locations, let's say. So these 3 are going to get, these 3 up here are going to get this triangle, and this one down here is going to get this triangle. So the pixel shader will be put into these slots, and then the pixel shader which runs for this big pixel is put into that slot. So I think there's some optimizations that a hardware MSAA will do, where it will like probably not actually store them out to main memory. I don't know what they do, to be honest, but there's optimizations that they do to save on actually writing them out, because that is very costly. So let's not talk about triangles, because we're not rendering triangles. So what we're going to do instead is we've got to find a way to run that pixel shader, which we're just in a compute, once, and then share it. So in our case, that sort of pixel shader is the material sampling, right? The ray tracing is the rasterization part, right? Those triangles were rasterized. So how we rasterize is we shoot the ray through the subsample, and we see which ellipsoids that we hit. And we wanted to do the transparency thing still. So the current plan is we still do, for every subsample, go over every single ellipsoid. and then, you know, build up a hit list, all the ellipsoids that we hit, and then early out when we reach something fully opaque. Reach accumulated opaque, or something which actually was opaque. We still do that. But rather than doing the material sample here, right, instead what we kind of want to do is take that bit out and do it later on as if it was from the pixel. So we want to build up a hit list, and if the subsamples share the same hit list, or the same set of ellipsoids in the exact same, they'll always be in the same order, but yeah, the exact same set of ellipsoids, then we only run the material. Yeah. To say if these three hit the same ellipsoid, so this really dodgy ellipsoid that does this, and you got another one which is like a little circle kind of thing, which is there. These three rays will build up the same hit list. So after you've done that subsample or subpixel, you want to somehow check if that list has already been inserted. If it hasn't, add it to some global hit list and store it for later. And then if it has, you just if it has, you would just up a weight, and the weight would just say, hey, there's another subsample which also has this, so multiply that color by, just do a weighted average at the end. Then this one you'll come across and be like, oh, there's not been anything with this same hit list, so add it to the global hit list. And then at the end, we'll go over all of the hit lists, go over all of the hits, and then material sample and blend front to back, and then compute the weighted average, so it'd be a bit slightly different code, and then we'll finally put that weighted average out to the screen. So you're doing less material samples here because you're sharing a whole array with neighboring pixels which are quite likely to share the same stuff. Now there's a further optimization here, and this is like something like this. Imagine if you had another object, ellipsoid, which kind of looks like a rounded cube. Anyway, it's an ellipsoid. Imagine that. So this is gone to these pixels with the same hit list and this pixel with a different hit list. This is still the same material sample. So what we actually need to do is build a list of which ellipsoids got hit separately from the hit list, right? I see this can be quite good. We can get some good packing down. And then we actually want to go over, do all the material samples first, because you're going to have, if you don't do it this way, and you just process each of the hit lists, you would process the same material multiple times. And if you have very high levels of, or high number of subsamples, like, 4x4 is 16 subsamples, and you hit the same stuff, you're going to be recalculating stuff you don't need, basically. So this would be a further optimization, and we should be able to get some good you got someone to blame, that's for sure. But it's my past self. Yeah. So yeah, we can get some good optimizations there as well. So this is gonna be pretty cool. We get to do some good packing, I think. Right. It's gonna be fun. So first of all, let's rename SSAA to MSAA, so we don't get confused what shader we're editing. Should have done the capital letters, but I can never tell which one is capital letters in or case sensitive or not. I know we're playing Astrobot. That soundtrack is great. The song I got in my head right now is that Funky Fungi? Is that what the level is called? Where you go through like caves and there's fungi moving around. Such a good soundtrack. Yeah, so right, here we go. This is where the fun begins. So we need a global hit list, and I think actually, right, since we're processing one sample at a time anyway, we actually only need one hit list that will just essentially move the cursor back every time it just doesn't get committed to the overall hit list. So I think what we need is some list of ellipsoids that have been hit, and then we need an actual sort of like yeah, we've got to be careful with these names because they're both. So I guess you can call it. Yeah, so you want a few different arrays, right? You want a hit. Call it e hits count. So you want to have some kind of maximum number of ellipsoids. So ellipsoids hit capacity. So what's the maximum number of different ellipsoids within a pixel that you want to allow? Right, and I mean like a full pixel, not subpixels. Like, because it's just one per pixel, one thread per pixel. Let's say 8. Quite a lot. I use a lot of registers, got to be careful of this. We can... Wait, what am I doing? We can probably, yeah, we can probably compress this down and get it to share a variable with something else. Yes, they might be able to reduce the registers on this one actually then. Yeah, you can probably reduce the registers here perhaps. Do some packing and unpacking. Maybe there's ways to free up some registers by joining two variables together and doing some bit tricks. Yeah, so you have the e hits, the actual list. Let's just say there's 8. You could probably you can't compress it down too much though. Anyway, that's a future optimization. Let's just get it working first. Now the other one is that there's actually another there's the hit list. Right, this is like a hit. Right, you want to have like a hit list entries, and you have a hit list count. Now you got to be careful because I guess Film Extension Visual Studio is no good because you have to. Yeah, I use custom Vim bindings. Yes, correct. So I would have to. Sometimes they don't all work nice. Yeah, I would have to like configure it. 1 and 2 the custom Yeah, sometimes those Vim emulators don't typically work as well anyway. Or there's more features in Vim which don't translate into Visual Studio, so it just doesn't feel. Yeah. You know, I do actually work in Visual Studio at work, so I'm kind of used to programming in it. But yeah, I do prefer modal though. Right, let's take a quick break. Yeah, be right back. Where's this music gone? All right, welcome back, everybody. Cool. Yeah, so we're trying to figure out how to build up these lists of things for the MSAA. Yeah, so we're after the sort of rasterization step in a sense. We're ray tracing some subsamples. We're trying to build up a bunch of things that we can use to build the we're trying to build up a list of hits, array of hits, and also all of the ellipsoids that got hit, so we can do the samples of the materials once. That is correct. We want some depths as well. I want depth. We need depths. Right, so within the so the hit lists, they kind of need to link. They could link, they need a depth and a hit. So you might as well actually link to this list here. And because this list is always going to be very small, you could actually pack it down into a very fine number of bits. So I've only had 8 maximum number of ellipsoids that I've hit. So that's like 8 layers. It's quite a lot. That's 3 bits, where I've had 4 per pixel. If we did 4, then that's only 2 bits. Then you could fit it. Then you could fit. So the hit list. Right, so what's the hit list got to have? So the problem is it's a hit list. That's the problem with it. So you could probably call it. Got to really be careful with this. Ooh, we could have a null bit. Yeah. Oh no, we can't have a null bit. Or could we? Right, let's figure this one out. So you want to have an array of which ellipsoid that you hit. So it'll be pointing into these arrays and indexing to there. And then you want to have probably a way to identify that you've ended that array, isn't it? So, you know, I was hoping you can use 2 bits because that will allow you to pack quite a lot of entries in. Wait, maybe we don't need that many. Yeah, you've obviously got, that'll give you 8 entries. Right, so if we had, right, so we could use some extra bits. I think, and we can have a special bit pattern, which will mean, yeah, right, so that's right, we can even make this number 8. Or how much we pack these numbers down. So if we increase the size of each hit list entry, let's say instead of taking 2 bits, it takes up oh wait, it was 2 bits, wasn't it? Your fit, where was it 2 bits per? Oh, it was 2 bits per, even more. Right, okay. Right, so we could probably get away. And 8 would be 3 bits. So I guess you 10 entries per 1U32. Huh. Maybe they could all just fit in a U32. But yeah, that's not even. That's not even. That's the problem with 8. You'd have to go do the next one. Where you say there's 8. Oh. Yeah, 16 entries, which is 4 bits. That'll get you 8. So you can fit 2 lists in a single U32 word. Right, so that's interesting, right? You can fit 2 lists in a U32. Like 4 lists this way. It's quite powerful. So if we just use up 4 bits for each entry within a list, and that is just going to point to one of these, or it's going to be a special number, which will mean that it's breaking, is stopping that hit list there, and then the ones that come after that are the next hit list. Yeah, it could be quite powerful. I wonder if there's a better bit pattern strategy we can do. Oh shoot, what did I do? Right. Yeah, I wonder if there's a better bit pattern. Yeah, so yeah, if we did 2 bits, we only get 4, but then we can't have a special pattern. Alright. Yeah, 4 should be enough. No, it's 4 per. Is it enough though? Let's go back to the super sample. So that had, in that hit list, it had a maximum number of 4 on it anyway. For one subsample. Whereas this is for all of the samples. All of the ones that you hit. So maybe we can make it 8. But then that's 3 bits. Let's make it 8 just in case. And let's see if we can do it. So, oh, and then you can use the bit at the end. No. Yeah, you can. 3 bits. And use the bit at the end. The 32 bits divided by 3, that gets you 10. 10 entries per U32 word. And you can use the... no, you got to do it divided by 4 of using the bit. The 4th bit. There's 8 entries. And you can use the higher bit to tell if there is another word that follows. Sorry, another entry that follows in this list. Yeah, that'll work. That'll work. Yeah, we'll go with this one. Right. Right, so hopefully that made sense. It will be explained as we implement it anyway. So essentially when for every subsample of the MSAA, we want to, and this is the rasterization step, we want to build up uniquely identify each ellipsoid that we hit. Right, if we hit the same one, we just don't bother inserting it, right? But if we hit a new one, we insert it in. This is a unique list. This one is if the subsample shares the same hit list, then it doesn't if it shares the same hit list, then it doesn't insert it into this hit list array. But if it if it shares it, it doesn't insert into the hit list array. But if it's not been in the hit list array, it will insert it in. So all of the subsamples that share the same hit list will just up a weight. So we want to have weights in another array. So I guess the idea is we want to figure out what's the maximum number of. So I guess why don't we should we not pack it down right away? Yeah, let's not pack it down yet. Let's write the code out first. So let me just write down what I thought about. Right, we'll use 4 bits. Right, use 4 bits per entry. The high bit signals that there is another entry in this hit list. 0 would mean go to the next hit list. Right, so let's just write that down to, for later. But for now, we'll just have separate arrays. So it's good to think about though. We can reduce the number of registers. So in terms of like how many hit list capacity. So if you can have a maximum of 8 ellipsoids, right, so the maximum number of actual lists, unique lists, let's say there's probably 4 of them. There's 4 different weights. We can compress that down into one U32 by giving 8 bits each. So that'd be pretty cool. Then the actual entries, the overall entries, you probably want to have a capacity of. So if it was doing 8 per word, we could probably get away with 2 words. So let's just say 16. Wait, there's 4 unique lists though. Oh. 32 would satisfy this properly. That's quite a lot though. We're going to experience some real bad performance if we don't pack it down. Hit entry, so the mask would be the 4th bit. So it'll be 8, wouldn't it, right? And then you want to know how many bits. That's 4 bits. Right, so say if entry this entry words is the number of entries divided by, if you have 32 entries. Yeah, I think we'll do the packing right away because this is not going to be performant otherwise. 32 entries divided by 4. Wait. It gives me 8. Right, size of E32 times 8 bits per byte divided by number of bits per entry. So that basically it's 32 divided by 4, that'll give you 8 entries per. It gives me the number of entries. I want the number of entries. Yeah, I want the number of words. So then that's this number divided by this number. It's 32 divided by 8, which gives me 4. We also need 4 words. That's quite a lot. Maybe we can change that around a bit, but this is getting a bit messy. So list entry words. Right. Weights. So the weights can be packed down as well into a single E32. Right, so you can just say the format is, it's packed into 8 bits per float. You can say 888 enum. No, not enum. Oh shoot, what is it? Yeah, there's some sort of scale factor on it. Like, yeah, you gotta find some 8 bits per weight. There'll be a weights scale and MSAA hit weight scale. So I don't know. There'll be some number. Wait, how do the weights work? The weight. So are you just incrementing it by 1 anyway? Is it actually floating point? Basically. So for every subsample of a, you're not gonna be left with anything transparent. It's a full. Yeah, it's just right. It's just an integer. Nice. You probably don't need 8 bits. That's all you need. 8 bits per weight. Bit overkill, but it'll fit. So you can probably fit the count in there, to be honest. The packing continues, and you probably put the pack in the loop. Put the weights in the higher bits and the count in the low bits. So when you add the count, it won't affect the higher bits. You can probably get away with, how many bits do you need? 4 bits for maximum number of lists. Oh, I'm getting confused. What is this? MSAA. Hit list capacity. So the number of hit lists is 4. That's right. So what you can do is store the number of unique hit lists. So the weight, MSAA weight, hit weight, I guess you want to say, you're going to do like against, oh, how do you want to do it? So you just want to be able to set it. How many bits will you need to use? We got a maximum of 4, so you need 2 bits. So you can probably do, that's the mask. Then you want to be able to basically set it. In the high bits of the value, you can store 4 of them. So that's only 8 bits you're using. Not a lot at all, is it? And then the rest of the bits can be, so the high bits, you want a way to store them in. You want a way to increment it actually. So yeah, this is the problem with the packing. So if you need a way to increment it, oh, that's not too bad. They always start off at 1 anyway. Yeah, you should be able to literally just get the mask and get the value, like actually get the value, and then just add the number, just add it on. As long as it doesn't overflow, it will be safe. Yeah, so you would say you mask it, you shift it to position, and then you just add it. So the shift would be weight index multiplied, so offset by so it's 2 bits. No, it's 2, isn't it? There's 2 bits. 2 bits multiplied by the number of yeah, by the weight index, and then that's shifted by, I think it's 24. It's just plus 24. Alright, that'll do it. Yes, that's all you need to do your weights. Right, that's pretty cool. You don't need the count anymore. There's a 2 bits per weight. Yeah. So we can just add stuff in there and that'll be alright. So we've packed that down. These ellipsoid depths could probably be packed down as well, but I'm not interested in doing that. I just wanted to make sure this was handled because this list could get quite high. Right, let's give that a go. So, what are we going to do when we go over all of those ellipsoids? Do we build up a local hit list? Or do we just append to this one? And do we just append to this one and then remember what it was and then clear the rest out again? We don't need to clear it all again. You might need to clear it. When you reset it. Yes, I think if you keep well, you can fit 8 entries in a single U32. So you fit a whole list in a U32 anyway. You don't need... Ugh, which means copying it in. You don't need the special high bit if you just say... Alright, I think we've gone a bit overkill. We don't have to do all of this. We can actually simplify it, and it should still be quite space efficient. You could probably get rid of this thing because it's a bit complicated, right? So you could probably say, hey, how many... These are the hit lists. Entries. Don't need that anymore, actually. You don't need that high bit anymore. Probably just use up 4 anyway. So instead, this is just going to be the hit lists. Right. So each U32 stores a list in it. That'll work. And then you got the counts in here. That's great. So you can check for equality just by comparing integers, like a full U32 int, which is quite effective. That's great. So that means the hit list locally can just be, do you have a local hit list? Which would just be a single U32. Initialize it to 0. And then when we go over every single ellipsoid and do a hit, we can just add it to this hit list. And then after that, figure out how to deduplicate it with this global hit list. That's right. That's good. I think the last time I needed a signed integer. The only time you need signed integers is when you're dealing with coordinates. But typically on a GPU, you use floats anyway, and floats are signed. You know, unsigned ints work with, you know, shifting right and left. Well, it's just shift right, isn't it? That's the different one. Shift right works properly. You don't have that invalid state as well. Extra invalid state, so you know you don't have to check if it's too big, not too small. Well, less than 0, you don't have to check. I was wondering if F64 makes no difference graphically. Probably not. It depends on the problem you're solving, but it's quite a lot more intensive. So it's not worth in that aspect. I guess Brian, are you a signed int fan? Because I know some people like live and die, but live and die by the signed int. It's one of those sort of like tabs versus spaces arguments. The reason why I don't use U16 or F16 because on GPU it's not widely supported. On my current card it is, but I want to maybe support some other cards that might not have it. But you know, by the time this game releases, maybe it's all gonna have it anyway. But yeah, you get some really great stuff on GPU where if you use a 16-bit in, you can actually just it uses half a register. And they got some special. Well, it okay. It depends on the hardware, obviously, but you can actually like, yeah, the compiler can do some smart stuff and just make it so that you're not using that many VGPRs. So pretty good. Right, don't like sign this fair play. Yeah, I'm on the same team as you. I'm liking this encoding, and you know, people like don't optimize prematurely optimize, but because I prematurely optimized, I managed to find out like, oh, the way we need to deduplicate this hit list with these hit lists is just an integer comparison. So it's not actually that expensive. I was thinking like, oh, I'll probably have to do a hashing function or something, but really it's already, you know, the whole hit list is in 1U32. Pretty clever. So if we go over all these ellipsoids, obviously there will be more ellipsoids in the future, but that ain't. Oh, we didn't even check transparency out. See how well that worked in the super sampled. Oh well. Anyway, so we get a hit. We need to figure out if it's a unique. If we've hit this ellipsoid on a subsample before. And the problem is you can have 8 of these guys, which is quite a lot. You know. Quite a lot, not gonna lie. Quite a lot of potential checks to deduplicate, but it saves you in the long run. Let's just write the code. We can optimize it later. Alright, so checking for hits. Have we hit this one before? Yes, we have. So, do what? What we do? Yes, I want to get some kind of like other index, we'll call it. We'll set it to this guy. Or maybe U32 max, whatever we want to do. And this one is going to be like, alright. Do a break. Right, hopefully we can optimize that down because I'm not a fan of that linear search. Over 8 potential targets. That's a good point. Should be using that instead. Right, if the insert index equals U32 max, then up the count after you have inserted the ellipsoid that we've hit. We need a unique set of ellipsoid hits. We might be able to use like a bloom filter maybe. I've heard about them. I've not looked into them, but they're ways of checking if they're definitely inside an array. Maybe we can use that to avoid the search. If it's probably not in there. But it might not be effective though because of inactive lanes and things. Depths. The depth it got hit at. So this one actually. Uh, yeah, we can run the same code. I guess that can boil down to this, which saves the crap. What was I saying? Which maybe saves the branching stuff. That might work. The depth you want to store in, good point, is a minimum. So we've got to be careful. You want to store the minimum depth. So if it's been inserted though, it's a bit problematic. So you kind of want to put infinity in there, such that this, then you got 8 of them. So you're putting 8 infinities in. But then again, in the grand scheme of things, it's probably not that bad. I don't know. In terms of what it's saving us later is probably better. So if we then say it's equal to the minimum between, because otherwise so here we're doing less branching basically because of that. We store tenia. Cool. Right, now if you've filled up this, your hit list is probably not. Yeah, we want to be careful. What do we do here? If E hits count. Right, I don't know what to do there. Let's just finish everything else though. So that just deduplicated the ellipsoid hits. There's quite a lot of work going on. Not a fan of it, to be honest. We can hopefully make that cheaper. Or the local hit list could probably be the local hit list could be it might be able to be a bit broader, and then you compile it down into a smaller list later, and then that would mean the search happens. Yeah, I think that's the approach we've got to take. So we might have to be, you might have to make an ellipsoid hit list. Local E hits. Will those put a depth in there as well? And then you deduplicate it, is that right? Later. Then you insert them in. But then you need like a lookup table. Gets complicated. I would try constant specialization or recompiling runtime to change values of intermediate instructions based on customizations, perhaps. No, I've not really tried them. Yeah, there's specialization constants that you can pass in when you compile a shader in Vulkan, but yeah. There are ways of doing like shader permutations without recompiling data as a whole and sending a whole new shader into the pipeline, but they're quite limiting, aren't they? So your shader has to, yeah, only scale by changing a single constant. And then hopefully the compiler does all the magic optimizations around that as well. Like gets rid of dead code or something, I don't know. Yeah, I've not really bothered with that. Hey there, Mo Overflow, how's it going? Because I don't really have many shader permutations anyway, and I don't think I will. I think I am going to have it with these guys, but they're just going to be their own shaders that are copied and pasted in. Does infinity become a problem when the float when doing graphics program? Do you check? I think shader programming does support IEEE floats, but yeah, it seems to be fine right now. I think though I've got to be careful on some hardware though. I don't know. Maybe it's okay these days, but it wasn't before. So I could just put in a really big number instead, and that could also just work. Yeah, so to save doing the search in the ellipse, like when you do the ray trace, not all things are going to hit same ellipsoid. So you could just poke it in a local array, and then later on go over a list of ellipsoid hits, try and deduplicate it into this list. And then try and deduplicate it into that list. As you remember playing old games and wrapping a variable like money counter past, sometimes it becomes negative number and you can't buy stuff. No, I've not seen that. That's quite funny. Yeah, but yeah, I guess unsigned would be better in that case, but it's funny. Negative. Well, it's interesting the game didn't crash. So either they knew it didn't happen or they got lucky. Or they thought it could happen. Yeah, I don't know. But yeah. Hey Alex, how's it going? Does anyone else hear popping sounds? Oh. Popping sounds? It's not good. I guess I'll just keep talking. I can't hear any popping sounds locally. I have it feeding back into my headphones. How's that cracking, is it? Right. Oh, I hear that. Is that better right now? I just moved the yeah, I did hear it, but I can't seem to hear it now, I don't think. That seems to be gone. Oh. Right, I'm talking into my thing, getting the feedback really loud in my ears, and I cannot hear the cracking. Right, well, I'm going to turn the music off. Can you still hear it? I think it's something that Windows, well, obviously OBS is doing. Weird. Uh, right. What about that? Anything going on? I guess has it only just started as well? How long has it been like that? Don't know what else I can do really. I can unplug my mic and plug it back in. I'm gonna try that. Right. That's the right. Right, okay. Well, if they ain't fixed it, I'm sorry. Best I can do. It might be that OBS is running a bit. I don't know. I think it's running okay. My webcam's a bit slow though. We'll let the music mask the rest. Right, so should we deduplicate the... Okay, that's cool. Well, as long as it's not too bad. Yeah, so should we deduplicate this array here, array of hits of ellipsoids? Should we do that here, or is there a quicker way we can do it? Um, so your threads within a wave are likely going to hit the same ellipsoids anyway, unless they're on the edge, right? In which case, you put them out into some extra registers. You have to allocate more registers that will be used in this lifetime. Then at the end, you can go over those and say if they hit different ellipsoids but the same number of ellipsoids, they'll run the same code. Right. The one of it will increase the register pressure, the number of VGPRs per compute shader, so it will run less of them. That's the issue. We've already got quite a bit here anyway, so I think we'll live with this for now. Right. But I guess if we did move it out, does this problem get solved? This problem might get solved easier. We'll think about that. But anyway, so let's add it to the local list. The local list, the way you do it, is this just how's it structured again? So there's a list of 4 bits. You can fit 8 entries in there. And then so it's 1 U32 per entry bits count. It's not 4 anymore. Oh, it's 4 bit. Yeah, it's 4 bits. Yes, you fit 8. You fit 8 entries in a what? Yeah, so all you need to do is so you get that insert index, right? You shift it. No. Right, so you get that local hit list. You OR that on. And just before you OR that on, you shift it by this guy. Oh no, after. I don't know anymore. No, first entry needs to go in. First entry goes in. And then you shift it. And I guess you do the check first. You want to say entries count plus equal 1. If it's equal to the maximum number, so for a list, it's got 8 entries. So before you shift it, if the local hit list entries is equal to 8, then we break. Well, I don't know. We've got to handle that. Right. Cool, we're doing good. See, maybe if we reach the maximum, and then on out we use the last one. That was we get some error. I don't know. We'll see. So anyway, we do the shift, and then yeah, that's it, right? Where's these alpha things? What are these doing? Yeah, so you accumulate the alpha if you reach opaque. You break. If you get the this is if you fill up the hit list thing as well. All right, okay. We'll do the greater than or equal to. It's technically more correct, but you'll never be greater anyway. Cool. Right, finally thought that through. So the next thing is we want to get that local list, deduplicate against the hit lists. All right, so I want to extract the weight. Sorry, the weight. Hit lists count. So you passed in the bits, and it's the first 24 bits, isn't it? So it's bits. I don't know why I need 24 bits, but it could be the first 4 bits. How many do I need again? I don't know. Anyway, 8, 16, 24. So you do a for loop over all those lists. And you check to make sure the list you've just built I wonder if this code is going to run quicker or slower than that super sampled one. The super sampled one is more simple, but we'll be doing far less material processing here. Yeah, if the hit lists list index is equal, right, we've just found ourselves another one. So we found list index found list index equals list index. So we can increment the weight and say, hey, there's multiple of us here that do this thing. So if found, gotta be really careful here. So in this case, the weight will go up. So there's a way you can say hit list weight. Hang on a minute. Yeah, I need to pluralize that to make it be correct. And count. Nice. So if we add, right, is where the magic happens. The MSAA hit. There's a shift you can get. So if you add the weight index, call it a list index, whatever. So to be careful, what are we doing? So we're trying to, it's the shift, isn't it? So you take the mask and you no, you want to take 1 and shift it by this. So it's 1. So the number of bits times the weight plus the base. Place of where it lives. Right, good. So you do 1 shift left. Right, and then you add that number on. And it shouldn't infect the rest of the bits because we never overflow. Yeah, we never overflow that weight. We've got some checks for that. Have we got checks for that? Well, we haven't. Yeah, we want to say, we would like to say, yes, the answer B is you haven't found it. You need to insert. And that is going to then increment the count by 1. Right, and the count's in the low bits, so you can just increment it all by 1 and it never overflows the higher bits. So the weights stay intact. That's quite cool. But you have the problem of this potentially overflowing. Right, because there's a set number of lists. So what you need to be able to do is handle the case where when found, when we haven't found anything, and if the next insert index, shall we say, I haven't even inserted the thing in yet, which probably right, so if it's equal to count, then check to see if the count is equal to the capacity of 4. Perfect. If so, we've completely filled it up. Bearing in mind, this only took the number of how many bits is done. If so, make your found index be whatever the last one was. So I guess you just, I guess more explicitly I can do this. I can just, yeah. And then, so if we have found one that's not the end, we just want to up the weight, increase the weight. And then here's the code where we say wait, sorry, what am I doing? This is this is where the insert goes, whoops. Alright, so that just ups the weight. So we just use the last it overflow or max number of lists reached. Use the most recent list. Then we just use the most recent list and up the weight. This one does the insert. The insert needs to say hit lists. Found list index. And then we insert our local list into it like that. So I think that's it. Ooh. Hey Ray March, how's it going? How you doing, sir? How's it? How's your project going? What have you been up to? What's the latency when sending DRAM to GPU? I wonder if you measured it. Not necessarily measure that one. It definitely varies between GPUs. We've not done that much intense perf testing. I wonder if there's situations when loops are faster than using SIMD on CPU because GPU transfer. Right. Well, in this case, these loops are using registers, right? They're all in VGPRs. So they're probably okay. But they're kind of like branchy and yeah. I prefer not to do searches like this, not gonna lie. Yeah, GPUs are pretty good if you're processing the same data across multiple threads. Yeah, they're pretty good at that. And the benefit that GPUs have is within a compute unit, they can have up to 10 compute units or more, depending on the hardware, right? They can park compute units that are fetching memory and resume another one which is ready to go, and then start going on it. So they can context switch. And this is why knowing you're using as little registers as possible is very beneficial on GPU, because the more registers you use, the more VGPRs, the vector general purpose registers, have been allocated. And there's only so many of them in a compute unit. So if a compute shader is live, then it's gonna have an allocation of VGPRs in the compute. Project's going good. I have a question though, and you'd like to know the answer. As someone who hasn't used a huge amount of Vulkan, is it true that Vulkan, the shader stage visibility you set for the binding when you create a pipeline, has to be identical, not a subset of the visibility? Yeah, it has to be identical, I think. Wait, you say visibility? Wait, you say visibility, what does that mean? When you set... So from my understanding... Oh, you're talking about the visibility. Right. Let me see what I do for mine. Obviously, I need to use compute, but let me just have a gander. I think HCC does it. I got an interop layer. I only use compute. Where is it? That pipeline stages, isn't it? Stage flags. Yeah, it's only passing computers as stage flags. Right. Yeah, I don't actually know the ins and outs of that one. I was thinking about, you was talking about when you change the pipeline layout. Or the pipe, does it invalidate different descriptor sets or whatever? Um, yeah, this is on the binding on what one it's visible for. Yeah, I don't know. You have to check the spec. They might be able to. I don't know. Oh no, 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 no. If you bind it, yeah, if you bind your graphics pipeline on the compute one, sorry, if you bind your descriptor set which has graphics things on it, it will work on a compute only queue. Pretty sure. I'm pretty sure that is how it works. But it could be wrong. It should work with a subset. Yeah, you just have to give it a go. I'm not sure on that one. Yeah. Right, so I think we've done the job now. Let's just double check this all makes sense. So we've got an array of ellipsoids that we've hit. And we've got an array of hit lists. Right, so it's a list of lists. Each U32 stores a list. And the indices point into this. So we get the MSAA coordinate, shoot the ray through the pixel, go over all the ellipsoids in order front to back. We've hit, search the ellipsoids for a hit. Oh, sorry, to see if it's already been inserted into the deduplicated set of hit ellipsoids. If you've found one, then insert, or up the count, insert into the array the ellipsoid index, and then min the depth. If we overflow the number of ellipsoids, what do we do? I think we would just leverage the latest one, the last one that you hit. Probably not going to happen. So you go if less than, and you do this. Else we shall just be like, well, the insert index is, let's take one. Cool. Maximum number of unique hit ellipsoids reached. Use the most recent hit. So then you add it to the local list by ORing it, adding one to the entries. If we fill it up, so again, it's got to do something like this, right? If it's less than, insert, which means potentially do a shift. Oh no, you always shift it before. Because there's 0 in there, you shift it before, yeah. Or it in, up the count. Then again, if you overflow, wait, you just do nothing. You do the alpha blend thing and then break when you... Nice. Yeah, so the super sample was like, it broke whenever you filled anything up. Whereas this is going to reuse things. Right, but if we broke, that could make another unique list. And then the alpha would be wrong, actually, wouldn't it, if we did that? So in this case, maybe we say... So in this case, what are you saying? Like, don't trace anymore? And just get a bit of sky? Yeah, but then if you reuse an old one, you'll probably get a different list. Which means that probably fills up as well. Hey, Trevor State, how's it going? Yeah, today's going good. It's pretty good. We did a super sampled anti-aliasing. It looks quite good actually, and the performance isn't too bad. I was quite happy with it, considering. So we're trying to do a more optimized MSAA in software, and I'm just trying to deduplicate data in a shader. So seems like a pretty bad idea, but maybe it'll work out. We've done quite a lot of optimizations to reduce the number of registers that we're using, but yeah, I don't know. We're doing some array searches and I'm a bit questioned about it. Yeah, I wonder if I can run the just get it to run the game of that. Oh, I've got screenshots. Good old screenshot tool. Hey, it doesn't save my past screenshots. Oh, that's a shame. Gotta fix that. Crappy sampling. Anyway, you can't. Not near sampled, is it? It's linear sampled, so it's blurry. Can't see the pixels. Anyway, probably drop it in Photoshop. Wait, I don't have Photoshop. Drop in Paint. Windows 11 Paint. It's just such a... Why scroll up to the top left? Like, just scroll where the mouse is. It's just... You not do maths? Anyway. Ugh. I don't know if you can make it out because it won't zoom in any further, apparently. But yeah, they look nice. I mean, this was 4 times super sampled. They look better. Yeah, we're trying to do MSAA, so we're trying to reuse some of the material samples and deduplicate things. But yeah, it's going alright. How you doing? How's the new home? Have you explored the new area? And you get familiar with the area? Oh, and in web GPU, interesting. It rejects it. Oh. Tracing is overrated. Yeah. I think if maybe slightly biased. But yeah. What's the difference? Yeah, they're basically the same thing. The lines are blurry, especially when you talk about voxels. Ray marching steps. Basically. Ray marching steps. But then in a sense, I'm kind of stepping array in this because I sort my ellipsoids front to back. But I'm still using array intersection code. So yeah, it's definitely blurry. The lines are blurry when it comes to ray tracing versus ray marching. Thank you. Yeah, PBR ellipsoids. Yeah, PS2 graphics. Yeah, when there's less TAA. Doing good as well. New home is nice, and yes, I've done some exploring and really nice neighborhood. Awesome. Very cool. Yeah, I don't really go outside much. We didn't really have, like, around where we live, a good place to walk. I guess we just, walk at the estate, and then we can walk to some park somewhere. We were on the outskirts of a town. So there's like a farmer's field, but unfortunately the field is quite muddy a lot of the time, so it's only really good to walk around in the summer unless you put some wellies on. And there's not really any good hills around. Whenever I go for a walk, I like a good hill. And then I sometimes go up the hill multiple times. I think all this graphics program and only games will ever make be low poly because I want to charge for it. Yeah, but you can still do some fancy stuff. Is that right? Do you have a beach? Yeah, I'm in the UK, right? So there's a beach kind of, not too far much of a drive. I guess if you're in the Midlands somewhere. But yeah, I'm in the southeast, so there's a beach. Beach is usually pretty close. So right, so we go over. Oh yeah. Max number of unique. So what do we do? If we fill up the max number of ellipsoids, unique ellipsoids per actual pixel, I guess it just doesn't matter. We'll just reuse it. I think the graphical anomaly will not matter that much. I think. Yeah. All right. Well, let's just carry on. Let's just get it working. If you fill it up, right? So if you fill up the number of entries within the hit list, you just don't insert it in there, and that's okay. Cool. And that's 8 entries again. Not likely. This is more likely to happen first. But anyway. Alpha blend the alpha. Just the alpha. We're not interested in anything else. Just the alpha. Because this is the rasterization step. We're just pre-rasterizing it. Getting some depths and some hits. And we'll do the material shading later. Next, after we've gone over all the ellipsoids, we get our little local list. We get the count out of there. And we go over the hit list. If we find a match, we break. If we didn't find a match, we and it's not equal to the capacity, we up the number of entries and we insert. Then this code here is going to say, well, oh yeah, so if we overflow the hit list, we just use the last one, and we'll up the weight if we ended up, cool. Right, so let's write the rest of the code and get it working. So this is all right. I'm happy with it. So we need to go over all the ellipsoids and perform material calculate the material things. The material color. We could probably pack the color down as well, I think. We'll do some smart stuff. So, So we're looking at sampling each material and storing a one for every. Yeah, these could probably be packed into some values and we can save some registers, but we've got to have a play around with that because I don't know. Well, there's a maximum of 8, so I reckon it's going to have some form of impact. So I guess you can call it e-colors. So you just say e-colors hit index like that. All right. So you've got your ellipsoid hits. That gets you your ellipsoid index. And then your ellipsoid depths. So you get your hit depth, you actually get your proper ellipsoid from the buffer. We don't really have a buffer yet, it's just an array. And then we get the closest hit position, get the vector to the closest hit from the ellipsoid, and then we get the normal. With the normal, we can do shading, and then we put the colors out into here. Bam. Now, final thing is to. Oh shoot. Yeah. This. The final thing is to go over all the hit lists. So we go for every list in hit lists weights and counts. Now you got to use that super lovely one of these. Extract it out of there. And then go over all of the lists. Now that's not enough. You got to go over every single entry within the list. Now you would have done the way we would have inserted them is done it front to back, which is a bit of a bug, I'm not gonna lie. And we don't store the count. So we've got to probably search. There's a maximum of 8 anyway. Yeah, you just say 0. If it's equal to 0. Right, I got it. So you go do another loop. And you do H index or whatever. These shorthand things. Yeah, run out of indices. Anyway, this will be. You don't have a count, so it's MSAA capacity. That's 8, right? Good. And yeah, maybe we should insert them differently. So we instead put them at the end of the list. Where's the insert code again? Here. So if instead, right, we shift right first, and then we, how many bits is it per entry? 4 bits per entry. You put it right at the end of the array. So you want to do 32 take 4. So you put that right at the end of the array. And then once you put it at the end of the array, you can shift the rest of the bits back down. So here, you shift the bits down such that so if that goes up to 8, you want to do that, take the maximum number of entries. I need to put a comment above this because it's a bit magic. Shifted by the number of bits. sorry, multiplied by the number of bits per entry. I think we've got to do take one or something, but this code basically, you know, shift the list. We say insert into the high bits, insert into the high bits, and shift right. Okay, shift right and insert into the high bits such that nearest near it the nearest ellipsoid such that the front ellipsoid is in the least significant bit. Right. That's good. So shift the local. Shift the local list down ends up in. Shift the local list down when the list is not full, such that the front ellipsoid is in the least significant bits. Right, so we take it's 8 entries. So say we had so I get, yeah, we want to be careful about 0 entries and stuff like this, I think. Careful. Yes, if you have 0, just shift right by 0, okay, that'd be fine. If you have 1 entry, it's in the high bits, you shift it by 7 slots. Alright, 7 slots, yeah, I think so. Yeah, times by number of bits. It's good, per slot. Cool. Right, it's a good change. So that means then this processing code only has to go until it reaches the 0. So you go if, so you take the list, the hit lists, list index, you go if list equals 0, we break. Now, you obviously want to shift it by the number of bits per entry at some point, but that's after you've extracted what you need. So what you need is the, wait, yeah, shift right. You want to extract out your, I call it the O index, didn't I? I've got a thing already for it. O. Did I call it an O? I think I did. Yeah. Right, so the O index is going to come from the list, whatever the hit list mask is. Where is that? Entry bits count entry mask, and the mask is 4 bits like that. Good. So you end it with a mask, and there's your O index, and now you can use that to fetch your you can fetch all the things you need, right? I think you can just fetch the ellipsoid index. So you go look at the e-hits and get your ellipsoid index, and then with that, well, we can get the colors. So you can then get the color, and then you do your front to back blend. Your color, call it C, I guess. The index rightio. You're going to get the... Alright, so... Yeah, there's a weight as well, isn't there? Yeah. So this would be your... I guess we can call it sample color. It's going to be blended with alpha. And you've got to actually fetch the alpha. So... Yeah. Call it color, I guess. Sure. So what we're looking at doing is front to back blend. Now you got to get the alpha. This is not very good. So I'm going to have to read that memory. Maybe it could be pre-populated into some registers. Again, it's using space though. So got to be careful. So we can think about optimizing that soon. And we're just getting the alpha there. It's not too great. So front to back blend. That hit list. Nice. Then if the alpha is not fully done, we'll front to back blend in the cube map. With that ray direction. Bear in mind, these ray directions don't exist anymore. So we're not doing it at the subsample level. So from this point onwards, we would like to fire or get a ray direction, not for these one of the subsamples. We want to get it for the main pixel. So we want to get the one that goes through the center here and not the subsamples. And we'll be sampling it as if it's the main ray. This is the MSAA optimization rate. Slightly incorrect, but it should be good enough. Yes, we get the view space ray, then move it into world space. These will then go full ham and do it through the center of the screen. This will, yeah, then use a sample cube map along that way as well. Good. Cool. Then with that final color, I guess I'll call it subsample. It's not really a subsample though. Anyway, then what you need to do is multiply it by some weight. So you need to be able to get the weight out. So the weight will be, so color needs to be scaled by whatever the weight is. So color, hit lists, and I guess I can make this into a float. Weight is equal to hit lists weights and count. There's a special macro because we decided to pack it all in to save down on registers. We get the shift. It's basically this logic here. Hang on a minute. Yeah, so we say, give me the shift that right by the list index. Right, we've got one weight per list. And we then want to mask. There's a mask on there as well. And then we want to add a total weight. Now the final thing we need to do is actually divide by the, which is here. What's that closest hit thing? Did we not get that as well? Right, so here's the division. Final color, which I don't know where that is, to be honest. Oh, it's way up there. Right, that closest hit, I can see where that can go. Put it down here again. Alright, so the final color can actually start here. Oh shoot. No. Final color. Right. Accumulates final color total weight. Divide by the total weight. Now this thing here to do with the closest hits, we have the depths here, range depth. So really we could be taking this one here and dropping it in here like this somewhere. Yeah, do we want the most transparent or the well, that's a good point. If you have hits, just use the closest hit one for now. Oh. Wait, it's just a store, isn't it? Nice. Cool. Right, but they're always infinity. So that means this could just be that, and then it only has to be used at the bottom here, like so. Cool. Right, I think that's it. That was a lot of work and optimization, but I think we've landed on something which is potentially good. But there is obviously going to be some more ways we can squeeze more performance out of this. Lots of like little loops that we're doing, which I'm really not sure about. So let's swap out for the MSAA one. Let's see if it compiles first. So this will just run the SSA. Right, my compiler's failed. I won't do the search, isn't it? Scene dims. Right, scene dims is in the global. Pass to a float vector. Then this one is saying that what? Oh. Huh? Oh, I need to cast the U chord as well. And this one's saying E colors. What's going on? H index. Oh yeah, I didn't change that. That could have been error prone. Oh, what did I do there? Oh, I didn't and it. What's the right and in there? Where is it? Beep. Hey there, sniper. How's it going? How are you doing? That's fun when you grow up immediately next to a beach. You can go everywhere, go there every day, especially also the population. Yes, not bad. Yeah, in the summer in the UK, it does get very busy down the beach on those sunny days. This is 4 times SSAA, but anyway, we know the shader compiles now. So let's go into SSAA. Or let's change it for MSAA. Yeah, it goes. Hopefully it works. Good, you? Nice, good to hear, man. Yeah, we're doing pretty good. Just been writing some anti-aliasing shaders. Alright, it works. Kinda. It only shows the edges of the ellipsoid. I just wrote a really expensive edge detector. Clearly. And the performance is nearly 1 millis, which ain't bad. It's only 2 times though. But yeah, I don't know why it's but yeah, I guess you can't really judge the performance. But it's only edge detecting the things from a bit further away. And getting closer doesn't really make the performance that much worse. Anyway. I don't know what's going on there. I guess we can check the code for bugs. But yeah, doing good. We made some good progress on this anti-aliasing stuff, and the performance hasn't been too bad. Quite happy with it so far. We'll see what happens when we add more ellipsoids, but it seems alright. I want to try another type of anti-aliasing though after these. I have 3 options I think will be good. Right, I did a lot of packing stuff, so it's probably that's wrong. Let's just double check every piece of code. Go again from the top. These are fine, it's just again a coordinate you're rendering and fine ellipsoids. Ray origin in viewspace is 0, then we move into world space. Get the dimensions of the MSAA by scaling it by the number of the multiplication along a single dimension. This is the unique ellipsoids that have been hit. I guess I can write the comment for it. Unique list of ellipsoids that have been hit or deduplicated. List of lists list of lists where each U32 stores 8 indices to the array above. Those 8 indices of the deduplicated ellipsoids above. Yeah. And you can say deduplicated lists of lists. Beautiful. Very elegant. Right. Now this is basically doing the rasterization. Rasterize the ellipsoids. Find all the ellipsoids we hit and generate hit lists. Front to back. each hit list stores Alright. Rasterize the ellipsoids, find all the ellipsoids we hit and generate hit lists. How far can you go just using static arrays if you make game plus engine? Well, if you just develop for a single platform like a PlayStation where you have fixed memory, typically your arrays are going to be statically sized, or you can get away with statically sized arrays and just allocate things. Because when you want to support multiple platforms, that's where you need the dynamic array a bit. Not really a dynamic array where you dynamically grow it, but in terms of like at runtime, you compute some size, which then allocates it at boot, and it doesn't resize. You can get away with that when using multiple platforms. But yeah, if you target like a fixed piece of hardware, you can get away with static arrays or statically sized arrays. Bro, have you used C++ for backend? Not sure what you mean by that. I program in C++ at work. I'm at home I program in C. So I don't know if that answers the question. But yeah, I write engine code and stuff. So find the MSAA coordinate in MSAA space, right? So scale in the scaled resolution. Shoot array through that. Pixel, accumulate alpha, initialize 0, no, eventually 0, list, initialize 0, good. Get the ellipsoid, do the ray trace. If we hit, try and deduplicate insert into the, that's good, into the ellipsoids array. If we haven't overflown, insert or, this is basically insert or overwrite. A good comment because I kind of forgot there. Maximum unique ones reached. Here's the most recent hit. This one is saying we're appending to the local link list or the local list. Linked list. It's not a link list. Don't worry. The local hit list. Shift right. So the first one it will be 0. So you shift and right zeros does nothing. This one adds it to the end. So yeah, shift right to store one entry in there. Insert index is always going to be quite small. So and we OR it in up the count. Nice. Front back blend. This all looks good. So looking fine for now. So it's for yeah. Then we shift right. So I guess if I can't find it like this, we're gonna have to do like printf debugging, which we can do. We've got some printing functionality in shaders, so it's fine. So what's this? 8. So typically you got a 1 in there. Like 1 take 8, 7. 7 times 4 is 28. Yeah. So shift right by 28. So let's just get the calculator up. As an example, we inserted a couple of bits. What is it? It would be 4 bits. We've got this number here. Wait. Their number. Yeah. Shift right by 28. Oh, it's too much. It's 28. Do we? Well, this could be the problem. Maybe. Oh, is that 28 in hex? I don't know. I bet it's 28 in hex. This got to do this, isn't it? You bastards. Right, yeah, okay, that code is right. Perfect. And that calculator. So you get the count. Store the count in the low bits. The weights are stored at the end. Yeah, so we can store 4. When you have 4 different lists. So 4 times 2 is 8, so you can fit them in there. You good? Right. So you get the count, go over all the lists and see if you've got an identical list. If so, we've found one. If we haven't found one, insert into the hit list. Right, you can just add it. Even though you got the weights in the higher bits, that'll work. If not, just use the previous one. Or the most recent list that's been inserted. Then if we right, I gotta be careful here. What are we doing? Is this gonna add a weight? Ah, shoot. It might add a weight when it shouldn't do it. So the problem is we're getting too many weights. The weights only need 2 bits. So it's got a value of 0, 1, 2, 3. There's times in it by 0, isn't it? And then like, oh, yeah, something fishy going on here. Wait, is there enough room for these weights? Do we need to allocate more? We can always allocate more room for these weights. It's not the big deal. The hit list, there's only a maximum of 4 lists, but you can have many samples that use the same lists. So actually, the number of weights that we want is actually more. We can use more. So we did 4 bits, that gets you up to 16. So on a MSAA 4 times 4, right? That'll get you 16. The 4 lists, obviously there's 16 bits. So if you have the first 16 bits, so you could overflow this weight though, that's the problem. So you really got to be careful. It's definitely possible to overflow the weight when you get into those high levels of and that will bump the weights next to you. Which is quite problematic. Yeah, maybe you just put the weights in a different yeah, maybe we'll use another register. Yeah, we'll use another variable, another register. We'll do that. So we did 8 bits per weight. That'll be plenty. So I don't need this count thing anymore. Alright. So what we're going to do is have the weights and have the count in a separate one. It's alright. Alright, we'll live with that. Right, so let's figure out. Let's just correct this. Oh, I've already got it. Cool, cool, cool. Going again. This one is trying to add the what's it doing? It's trying to extract the weight. We get the weights. By some shift based on a list. Index. Yeah. And we end with a weight mask. So the weight mask is FF now. So it's one byte. Right, let's keep going. Oh, that one. Right, it's already there. This ups the count. And this ups the weight. Right, that's cool. Oh, gotta be careful. Where do I use this weight shift? Oh, I've already done that. That's good. That's good. Cool. So let's go back to where we were. Try and correct that. So, yeah, this is where we insert the weight. Wait. Oh, I was down here, wasn't I? Right. So what we're saying is if it gets inserted, right, that found is not going to be equal to the list count because you would have upped it, which means then this is going to add 1. Right. But I think you're always going to add 1 because you've got that special thing here where it always puts it in bounds anyway. It's good. Right, so we up the weight. Nice. So that's all fine to me. So now it's the next bit of code. Yeah, so what other bit shifty stuff we got? That's everything's kind of looking alright there. Right, so we go over all the ellipsoids here and we're simply just right, the colors are just initialized. So we get the ellipsoid index and the hit depth, and we get the ellipsoid and do the shading. And put the colors out here, the shading color. I got the total weight, final color, go over all the lists, pull the list out. Get the color, go over all the hit entries. If the list is empty, we'll break. Take the entry out. That gives you the ellipsoid, the local ellipsoid index. You then take that and get the proper ellipsoid index. That is wrong. Wow, that was an index. That's why the color was wrong. That maybe that's why the color was wrong. I don't know though. Pull the color out and then use the ellipsoid index to get the ellipsoid. We could probably get rid of this code, I'm hoping to. Right, then we take the list down. Good. Is this Buckethead? No, this is Stone Rebel. Stone Rebel, pretty good group. Right, if we didn't get an opaque or reach opaqueness, if that's even a word, we sample the cube map and then again blend front to back. Then we take the weight, because multiple samples could have the same hit. Yeah, the multiple samples are probably going to have the same array of hits. So we take that. Right. We extract the weight. Nice. And then multiply the color by the weight, accumulate the color into the weight, divide. Yeah, you're probably better off doing. No, let's do the optimization before I forget. It's a scalar across a vector, so it's gonna improve as 4 floats. And output it. Good, let's give that a go. Hopefully it's fixed it. Hey Voodoo. Yeah, on Windows because I installed a new GPU and then Linux was like, it didn't want to work. So I'm gonna have to reinstall my Linux, which is a damn shame. Right, so apparently we hit a shader error. It's running, but it's got a black screen. I don't know what I changed. I changed the number of changed how the weights were done, and I changed how the I changed that O index thing on it. Yeah, it's correct. Correct. And I changed the way changed the way the weights were stored. Is that in bracket? Oh, for crying out loud! No. Yeah, it's in brackets. Right. Hey Valvas, how's it going? At least now I'm gonna lose the stream and shader is bugged. Well, that's the thing, we're not gonna do it anymore because I installed that new GPU. It's not because of Windows. Windows was still blue screening. So yeah, hopefully, right? Fingers crossed, right? It's not gonna completely destroy the stream. It's not been doing it so far. I think that was a case where it would have done it. So I think maybe we've got some infinite loops somewhere or something, and it's done. Yeah, maybe debugging would be nicer. I would hope. You know, it still runs. I've never seen it get a device lost yet, even though I've got very limited time with it. So I don't know what's. My ideal thing would be maybe it runs the code up to the exception, or you know the seg fault or whatever, and then maybe I could do some printing before it does it, which would be really incredible because I've not had that experience before. Although black screen isn't very nice. You left the division at the end. Oh, I didn't know. Thank you. There's me, premature. Okay, we have one premature optimization win. And now we've got a bit of a. Oh. That's a good point, though. We did change that. I don't think that's the cause, right? That looks pretty correct to me, but let's just try that again. I don't know why it takes so damn long. It never used to take this long. Anyway, like it. Yeah, I'm getting kind of tired right now, and I think it's time for me to eat some dinner, and then I'll crash out. But good progress today. We basically wrote two anti-aliasing shaders. This one is nearly there. I can feel it. So I think next stream we'll finish this one off. We'll maybe do a bit of performancey stuff, but we have got so the overall plan is we want to investigate, bring back anti-aliasing. So we've got another one that I want to do is do ray traced anti-aliasing, and we've done it in the past with a sphere. So I want to sort of like do that again, but with the ellipsoid. So this one is going to work at the standard resolution. It's not going to do any of this sort of like upsampling thing. Oh, no, sorry. It's not going to do any of this super sampling type of business. Instead, it will check how close the ray missed or nearly missed, and then fade the pixel out and do a transparent thing. We also haven't tested out transparency either. So yeah, I think we'll do one more stream of, it might be two more streams. Yes, Tuesday and Thursday are probably going to be this AA stuff still. And then we'll do a stream on Sunday, which will probably be something else. Maybe we'll try and get multiple instances going and stuff like that. And yeah. Yeah, probably wrap up these next week. Hey, what's going on here? You don't need the parentheses around. I'm always careful when I mix. Yeah, that is kind of true. Those shifting ones. What's going on? Where's this? Yeah, I'm always careful too. Right, this is the AMD code, and they seem to do it there for the equals. But yeah, I'm always very careful with the shifting ones too. They don't really make sense, do they? Seems alright. Give that a go, see what happens. Yeah, so next be on Tuesday and Thursday, and then I don't know if you can really see that, but Tuesday, Thursday, probably about 2.5 hours ago. Wait, I can't even do maths right now. Yeah, it don't work. Probably about 3.5 hours ago, 7:30 GMT. And then Sunday is probably about 5 hours ago now, however long the stream has been going for. But yeah, thank you for everyone who's supporting me. Close the Git. I'll put it up on the Git tonight. I'll get it up there on the GitLab. And yeah, if you want to support the stream, you can get on the Discord and get access to the code that way. Right. Oh, I'm hungry. Let's find someone to raid. Thank you so much for coming, guys. I hope you have a good start to that work week. Raid Artie. Artie's pretty cool. I like Artie stuff. Making his own game. Right. Got some procedural generation as well. Fancy stuff. But yeah, have a good start to work week, guys. See you in a future one. Much love. Bye-bye.